Okay, finally, I think I've made this work. I spent way too long on trying to make this work, but I think I've done it. All right, it's time. Goddamn, I've. All right, so okay, we have a pretty long document here, 39 pages, and we're going to go through the entire thing. We're going to talk about halogen and alkanes here. This first part, it's I think consisting of 9 parts ish, and yeah, the first part I'm honestly introducing to halogen alkanes. I'm kind of used to it already because I kind of went through this on my own, as well as the second part, a little bit of it. Um, but it's okay, and we're gonna go through this really quick. So yeah. So okay, I know if maybe you'll notice there's a little thingy over here or something like that. I just put that there for fun. Maybe it'll be kind of interesting to look at. But I might sometimes accidentally write over that, and if I do that, I'm sorry. Hopefully I'll scroll over it or something. But yeah, okay. So yeah, introducing halogen alkanes. This is going to be IEL chemistry, and whatever else. We'll just talk about it later. So it has two names. Haloalkanes are alkyl halides. As of right now, I don't know why it's called this. I know that alkyl groups are called your CH3 and CH2 or whatever, your CH2, CH3. Those are called your alkyl groups. Halides is halides. Haloalkanes, I'm pretty sure, is just a short form of halogen alkanes. Okay. Um, okay, specifically right now we're going to be talking about what they are, physical properties. Okay, so what they are, physical properties, and also chemical reactivity. Then details of chemical reactions are described later on. Fluoroalkanes are extremely unreactive, so we shall mostly ignore them, other than just pointing out why they are. So, what are halogen alkanes? They're compounds in which one or more hydrogen atoms in alkane have been replaced by halogen atoms. So, we have a normal alkane, so we have, let's say, the skeleton, and has two H's in each one, and this one has three H's. So, three H's here, two H's here, here, here. And one of the hydrogens is going to be removed and replaced with a halogen. Okay. Now, for the most part, we will only be looking at compounds containing only one halogen atom. So we're never going to be looking at one alkane with two halogen groups. We're not going to be looking at that. For example, we have here, um, right, you're going to be looking at the namings. This is the most important part. So over here, when you have an iodine, we're only going to be talking about three halogens here: bromine, chlorine, and iodine. And then there's also fluorine, but again, fluorine is mostly unreactive, so we don't talk about it. Iodoethane is the name for iodine, chloro is the name for chloro, and bromo is the name for bromine. Um, this is also a little bit of pre-existing knowledge. I did study a little bit of halogen alkanes in P1, and also knowledge of basic of your alkenes, alkene reactions will help you in halogen alkanes because of course it's organic chemistry and there are some certain principles which carry over. One of the most outstanding principles here is going to be your this, of course, your naming, and also some topics are going to be carrying over, a lot of actually, from IMF forces. I think that was topic 7. So starting off with different types of halogens, we're going to have 3 different classes, and these going to depend on so there's going to be your independent and your independent variable and your dependent variable. Okay, I'm going to be explaining things like this often. Okay, so over here, what are we changing and what is going to get changed? So in this area, we're going to be changing where the halogen atom is positioned on the chain of carbon atoms. That's what we're changing. What's going to be changed is the chemical differences or chemical properties of these certain types. Now, first of all, primary halogen alkanes. We're going to be calling them haloalkanes. So primary haloalkanes, the carbon which carries a halogen atom is attached to only one other alkyl group. Again, an alkyl group can be a methyl, CH3, or CH2, which is going to be your ethyl. And that's going to be your alkyl groups. Alkyl groups are usually they're short formed into R. Okay, that's what their symbol is. So whenever you see RX, that's going to be your alkane or your alkyl group. So that can be any type of alkane with their halogen group going to be X. Okay, so over here we're showing halogen alkanes with primary group, primary structure, And again, they said that they're only going to be bonded to one other alkyl group. So over here, you can see this is only bonded to one. This is only bonded to one. This is only bonded to one. Notice how this gets these are getting more and more complex as you go. First it was just CH3, now it's CH2. First methyl, ethyl. Now it's methyl with. Now it's propyl. Wait, no, it's not. It's more than that. It's 1, 2, 3, 4. So that's gonna be your butane, ethane, methane, butane, propane. Propane plus the branching at the second. So yeah, name it and whatever. So notice how no matter how complicated it gets, it doesn't matter. In each case, there's only one linkage to the alkyl from the alkyl to the halogen. So yeah, it's going to be considered primary. Now there's only one difference is in CH3Br. They're often counted as primary halogen alkenes, even though there are no alkyl groups attached to the carbon. Why do we say that there's no alkyl groups attached to the carbon? Because in CH2, in this, what we're having, actually, I have to look into this, because even this I got kind of confused on my first time around. Oh, secondary halogen alkanes. So this is yeah, secondary halogen alkanes. Two other alkyl groups, pretty self-explanatory. Tertiary, three alkyl groups. Now the physical properties. First physical property that we're going to be looking at is going to be your boiling point. Now usually your physical properties is going to be your dependent variable. It's what changes, and what do you change which causes that change is going to be shown. So over here we are noticing three, first of all, straight up, we're noticing two different independent variables and one dependent variable. One dependent variable is going the dependent variable is going to be your boiling point. Your independent variables are going to be one, the length of the molecule or the atom. Again, X is going to be your halide, and then the type of halide used. Okay, from chlorine to iodine, we're going down the periodic table. Okay. If you want to know, fluorine would be above all of these. Okay, fine. Notice how over here we have gas, and just know that there's a room temperature limit down over here, which is denoted with a green line. And so when you're going up and when you're increasing, okay, so some basic things. As you're increasing the size of the molecule, we're noticing boiling point goes up. As we're going down the group, we're going down group 7, we're noticing the the boiling points go up. So those are two things that we're noticing. Some notes to take is this is a gas. Naturally, as a natural form, these will stay as gases. I think the notes explain it better. So these have boiling points below. Three of these, this have boiling points below room temperature, and these will be at gases at room temperature. Okay, so the other you're going to be coming across as liquid. Remember that the only methyl halide, as in the only halide which exists in a liquid form, is iodo method. Okay, so which is going to be this. Okay, so when you're looking at methyl halide, you're going to only have three options to choose from. Which one is going to be liquid? It's going to be your iodine. Your chlorine and your bromine are both going to be liquid at your methyl stage. Methyl has been being the first carbon, ethyl being the second, and butane. Well, butyl? Yes. Chloroethane is gas. Yes, and when you're talking about ethane, chloroethane is going to be your only gas here. Okay, now the patterns in boiling point reflect the patterns in intermolecular attractions, meaning that what's changing here is going to be your intermolecular attractions, and what's going to be changed due to that is going to be your patterns in boiling point. So first of all, intermolecular patterns, we're going to have, if you, what is going on here? I hope this is okay. Intermolecular patterns, you're going to be linking to your topic about intermolecular forces. So what are the three intermolecular forces we talked about? We're talking about dispersion forces, van der Waals. We're talking about dipole, permanent dipole forces. I'm not very 100% on that topic either, but I'm happy on it. Thank you very much for asking. Um, um, is this going clean? Okay, yeah, it is going clean. I hope everything's okay, man. That would suck if it wasn't. Okay, so yeah, van der Waals dispersion forces is going to be your first thing that you're going to talk about. There's going to be your dispersion forces and going to be your dipole forces that you're going to be talking about here. Of course, not hydrogen bonds, because there's no OH here. There's only H's. So, simply put, as we already mentioned, they get stronger as the molecules get longer. As we saw, the molecules got longer and the boiling point went up. As the molecules get longer, they have more electrons. More electrons increases the size of the temporary dipoles that are set up, which then causes the attractions to get stronger. So again, molecules get longer, more electrons are present because MR increases, and that increases the size of the temporary dipole, which causes the attractions to get stronger. What kind of attractions? Attractions caused by dispersion forces. This is why boiling points increases the number of carbon atoms in the chain increases. Look at the chart for a particular type of halide, chloride for example. Dispersion forces get stronger as you go from 1 to 2 to 3 carbons in the chain. It takes more energy to overcome them, and so the boiling points rise. The increase in boiling points so this is talking about. So let's mark this as let's mark this as 1. So if you look over here, what we're seeing is this is 1. As we're seeing, as the molecule gets longer, MR increases, more electrons, and so the boiling point increases as the instantaneous or temporary dipoles that are set up gets increased in size. Okay. Now, yeah. So they get stronger. Dispersion forces get stronger as you increase the number of carbons, increasing the number of electrons, and so it takes more energy to overcome them, so the boiling points rise. This is classic IMF stuff. Now, the increase in boiling point as you go from a chloride to a bromide to an iodide. Now we're talking about element to element rather than the size of the alkane chain. This is also an increase in the number of electrons because we're getting a bigger element. We're going down the group. So as we have a number of electrons increasing, that also leads to larger dispersion forces. Of course, there are lots of more electrons in iodomethane compared to chloromethane, because again, iodine is a larger molecule than chlorine. So if we mention this as point number 2, can you see 2 over here? Oh, barely. Okay, I gotta be careful. If you see over here, now you have 2. Now you can see that bam. Yeah, as you go down the group, as you can see, as we go down the group, the thing only increases because iodine. Because as you go down the group, it gets larger. There are more electrons, right? So yeah. Now, talking a little bit about dipole attractions, carbon halogen bonds, right? So dipole attractions again. If you remember, that's talking about your polar bonds, your electronegativity, that kind of stuff. So your carbon halogen bonds, apart from the carbon iodine bond, are polar. So just remember this for now. This is not too important, but just remember it for now because we're going to explain it a little bit later. So apart from the carbon iodine bond, your carbon halogen bonds are going to be polar. So since it's polar, it's polar due to the fact that the electron pair. So if you look at C and if you looked at X, right, or if you looked at C, which is the CH, which is the alkyl group that the hydrogen is bonded to. If you see this, if you see the bond and the pair of electrons that is shared between these two, it's closer to the halogen, because the halogen is the more electronegative one if you look at the periodic table, right? And since since it's pulled closer to the halogen atom than the carbon, the bond is going to be polar. Okay, so if you look at the electronegativity values, first you have F, then you have Cl, then you have Br, and then you have I. And if you notice, I is going to be the same electronegativity as C. This is why the carbon iodine bond is not polar. It is not polar, but it is still it is not polar. The rest are, fluorine is going to be your most electronegative, so the most polar, and bromine is going to be your least polar, And this is not even polar. This is not even polar. Okay, this is a non-polar bond. Okay. So if you can imagine, since the electronegativities are same, if you look like a Ci bond, the electrons would be perfectly in the middle. So this is a perfectly non-polar bond. This means that addition to the dispersion forces, so alongside the dispersion force that we talked about before, there'll be forces due to the attractions between permanent dipoles. Okay, so what they're saying is alongside dispersion forces, there's also the permanent dipole forces, except for the iodine case. Iodine will only have dispersion forces to guide it or to help it increase in boiling point. Now the size of these dipole forces will fall as the bonds get less polar, obviously. As you go down the group, they get less negative, electronegative. Chlorine, bromine to iodine. Iodine is the least electronegative. Chlorine is the most electronegative. So as you're going down the group, it's getting less electronegative, so the dipole-dipole attractions will fall. However, the boiling points will still rise. As you know, polar bonds will be stronger, right? As the polar bond increases, then your permanent dipole perm will increase. As your permanent dipole increases, then the force will increase. As your force increases, it gets stronger. However, and as we go down the group, we notice that that all of these will decrease, right? But although all of those decrease, we still see that as we go across, that it still increases. There's still an increase in boiling point. That means the energy yet still increases, and the only explanation for this will obviously be that although the permanent dipole attractions is decreasing, it is not as strong or it's not as important than the temporary dipoles which are caused by dispersion forces. The dispersion forces are just that much stronger or that much more important or valuable to the haloalkanes strength, etc. Like the strength of the bond, how much energy it takes to break it. Now, the large increase in the number of electrons by the time you get to iodine completely outweighs the loss of any permanent dipoles in the molecules. So you can think of it as, two variables. One is going to be the number of electrons you have. Another is going to be the electronegativity caused by the permanent dipoles. So as you go down the group, although your permanent dipole, your polar and your perm dipole are both decreasing, your electron number is increasing, and so the boiling point will still shift to increasing because the electron number which relates to the, oh shit, can you see this? Oh my god, just barely, holy crap. Oh, okay, I'm gonna just make this a bit smaller, because this is just not worth it. I want you guys to see this shit, because I'm cooking over here. All right. Okay, so so as electronegativity, electron number will deal with dispersion, and dispersion just has a better say and much more say than your permanent dipole. And so the boiling point will still increase because these increase, and so the dispersion forces increase. Now, boiling point of some isomers. Isomers, again, you're going to be your same MR is going to be equal, but the position of the bromine is going to be different. And if what did we talk about before regarding the position of the bromine is going to be your kind or your type of halogen alkane, right? It's going to be your primary, secondary, tertiary. In this case, you can notice there's only one bond here. There's going to be two bonds here. There's going to be 1, 2, 3. The alkyl group is bonded to 1. This alkyl group is bonded to 2. This alkyl group is bonded to 1, 2, and 3. So this is going to be tertiary. This is going to be second. This is going to be prime. Okay. Primary. These are the slang. I'm just using the slang if you're new to the chat. And we're noticing that the boiling point will decrease as you go down these. Okay. Now, boiling points fall as you go down from primary to tertiary halogen alkanes. Now, this is a result of the fall of effectiveness of dispersion forces. As you remember, dispersion forces not only was the electron number which was important, but also the surface area slash how close it is, like distance, surface area and distance from the other alkane, or the other, how do I say it? The other atom, right? So here, the temporary dipole forces are greatest for the longest molecule. First of all, this one, and the attractions are also stronger if they can lie closely together. Now, if you have a longest molecule, obviously what's going to happen here is you're going to have the largest surface area. And if you have the largest surface area, then you're going to have more areas of, you have a greater chance of forming an instantaneous dipole if you have a larger surface area. Instantaneous dipoles are formed when in contact with other atoms or other molecules. So when you have a longer molecule, you're going to have larger surface area as compared to a smaller molecule with smaller surface area. And also, if it's straight without any branches, then if it's branched and if it's straight, don't imagine this as a skeleton. Imagine this is as the actual thing. If I have another thing and it's going like this, okay? If I locked these two together, these would not fit. There would be a huge distance between here and here. However, if we had, and these are two super branched ones. But however, if we had two of these would go almost touching, unless they're actually touching. And if the distance between these two are very small due to their extremely, long and branchless chain, they're very thin and they're very long, then you're gonna have stronger attractions because they're just closer to each other, right? And so they're strongest when they are long and they are thin. Tertiary halogenalkanes are short and fast, so they won't have contact, and also their amount of permanent dipoles will just be less because they have less contact. So it becomes it has the least boiling point. Now we're talking about some reactions almost with other with other elements. In specific, we're talking about dissolving in solvents, and the first solvent that we're talking about is going to be your water solvent. Okay, so halogen alkanes are at best only very slightly soluble in water. Why is this? Well, so when I say the word at best, it means it's mediocre. It's not very good. And why is this? So in order for halogen alkane to dissolve in water, you have to break attractions between certain things. Okay. If you want two things to bond, but these two things are already bonded to certain things already, you need to break those two things so that they become their free particles so that you can bond them together. Okay. Now, in this case, the bonds that we have to break is going to be the bonds between the attractions, the ones that we talked about, the permanent dipole and your dispersion forces between your halogen and alkane molecules. It says right here. And break the hydrogen bonds between the water molecules, correct? Because water can form hydrogen bonds with each other. So you have to break those, and you have to break the hydrogen, break the attractions between the alkyl group and the carboxylic, between the alkyl group and the halide. If you want the halide to be dissolving, or the entirety of this thing, in fact, if you want the entire halogen alkane to be dissolving with the water, breaking both of them cost energy. Now, energy will be released, of course, when new attractions are set up between the halogen alkane and water molecule. So if you're wondering, okay, now is this process exothermic or endothermic? What is more, the energy released or the energy absorbed when breaking the bonds? Well, you can understand that here. The energy released will only be the dispersion forces and the dipole-dipole interactions. Oh, sorry, I'm so sorry. It says the energy released will be formed from the new attractions that are set up, and the new attractions will be dispersion forces and dipole-dipole interactions. Of course, no hydrogen bonds will be formed because there's no OH group in halides. So, since these aren't as strong, of course, hydrogen bonds are strong, so if these aren't as strong as the original hydrogen bond in the water, as not as much energy is going to be released as it was to use to separate the water. So what they're saying is what the energy released is not going to be as much as the energy taken in, mainly because the hydrogen bond is going to be much stronger when you take in energy to break the hydrogen bond. Since no hydrogen bonds are being formed, the energy released is not as much. So the energetics is sufficiently quote unquote unprofitable, so very little dissolves. Since again, you're putting in a lot of energy and not getting that much energy out. You're putting a lot of energy in and you're not getting that much energy out. It's unprofitable, and so it doesn't happen that much. There's also stuff regarding entropy, but of course we don't know that, so we're not going to talk about it. Now, solubility in another solvent is going to be organic solvents. Okay, they tend to it's a greater tendency to dissolve in organic solvents because new intermolecular attractants have much of the same strength as the ones being broken. So the energy taken in to break it and the energy taken out, when the energy released when making, are going to be relatively equal. So it's going to be it's going to tend to dissolve much more. It's going to tend to dissolve much more. Chemical reactivity. So now we're going to be talking about the reactivity of halogen alkanes. Of course, chemical reactivity is going to be your dependent variable. Let's see what the independent variables are. First of all, they're saying the patterns and strength of the 4 carbon halogen bonds. So we're starting from CF to CI. Notice that the bond strength falls much more when you go from CF to CI, and notice how much stronger the carbon fluorine bond is than the rest. Now, what do I mean by this? So, okay, we're looking at strengths. We're not looking at boiling points. So we're looking at strengths only, and we're seeing the CF is much higher than everything else. Huge gap when you go from here to here, and not that much gap, but the gap does decrease as you go across. Now, in order for anything to react with halogen alkanes, the carbon-halogen bond needs to be broken. The carbon-halogen bond, not the attractions, the bond itself. Okay, notice that. When we talked about dissolving, you didn't need to break the carbon-halogen bonds. You only need to break the attractions between the carbon-halogen bonds, between the carbon-halogen and other things. Okay. This time you need to break the carbon-halogen bond itself, and because and since you go from fluorine to chlorine to bromine to iodine, the bond gets weaker. It becomes more reactive because it requires just less energy. Since iodoalkanes are the most reactive and fluoroalkanes are the least, in fact, fluoroalkanes are so unreactive that we shall. Okay, so again, as you get a stronger bond polarity, you're going to have a greater strength of the bond, so it becomes less reactive because you just don't have enough energy to break that often than not. But talking about it more specifically, influence of bond polarity. So what they're saying is bond polarity is going to be your independent variable in this case, the influence of that on your reactivity, aka your strength, but whatever, your reactivity. So the influence of bond polarity on reactivity. Now of the 4 halogens, fluorine is the most electronegative, iodine is the least. This means the electron pair carbon fluorine will be dragged the most. As you can see, it's dragged the most, and iodine is literally in the middle, as we stated before. Okay, as you see, the delta positive and the delta negative is getting smaller and smaller and smaller until it's literally not even there. As you go from fluorine to iodine, the electronegative negativities of carbon and iodine are equal, so there will be no separation. One of the important set of reactions of halogen alkanes involves replacing the halogen with something else. This is going to be one of your most important reactions. We're learning about halogen reactions, and this is going to be a very important one. It's going to be substitution reactions, where you have your halogen and it's being replaced by something else. Okay, that means that these reactions will involve carbon-halogen bond breaking to give positive and negative ions. Right. So when you have carbon and you have your halogen, halogen is going to be your most electronegative. So when this breaks, your halogen is going to be negative, your carbon is going to be your most positive. The ion with the most positively charged carbon atom, as in the ion with the most positively charged carbon atom. I don't know why they worded it like this, Anyways, the positively charged ion in this situation will be your carbon, and it reacts with something that's either fully or slightly negatively charged. So then your positive chlorine will be bonding with something that's negatively charged, which is not going to be your halogen. Something either fully negative or negatively charged negatively charged attracts the slightly positive carbon atom and pushes off the hydrogen. So as in when you have CH and it's already a dipole, so you have your positive and you have your delta negative and something's coming in, which is something negative. Something negative is coming in, and when it comes in, let's say your OH is going to be your negative. As it comes in, it's gonna kind of like shove off the hydrogen, okay. There's going to be some homolytic. No, that's going to be heterolytic fission, right? So you're going to have some heterolytic fission. This halide is going to break off, and you're going to have your carbon bonding with your OH, okay. Now you might have thought that either of these would be more effective in the case of carbon fluorine with quite large amounts of positive and negative charge already present. What they mean by this is that, honestly, do I know what they mean by this? You might have thought that either of these would be more effective, as in one is more effective than the other in the case of carbon fluorine with thing. But that's not so. Quite opposite is true. The only thing that governs the reactivity, the strength of the bonds, is the strength of the bonds which have to be broken. I think what they're trying to say here is you might think that this will make the thing more reactive than this, or this will make the thing more reactive than this, but in reality, the only thing that will determine the reactivity is the strength of the bonds and how easy it is to be broken. As the easier it is, the more it's going to be reactive. Alright, that's going to be your first topic. I'm going to take a little break and I'll be back. Alright, we're back. Oh my god, I'm blushing. Because this is my favorite chapter. No, it isn't. Okay. Making halogen alkanes. Finally, we're making this shit. I'm actually excited. Actually, I'm actually blushing. Yeah. Yep. Okay, fine. Let's go. Covers. Making halogen alkanes in the lab. Starting from alcohols. So we're going from alcohols to halogen alkanes. Okay. Covers more than enough detail for UK level purposes, but it isn't supposed to be all inclusive, of course. Summarizing the methods of preparation. Halogen alkanes can be made from the reaction between. This is all new stuff to me, by the way. Can be made from the reaction between alkanes and hydrogen halides. Hydrogen halides as in your H plus your halide group. It's better if I write this as in your X group and your H group. Reaction between that hydrogen halide and also your alkenes. Oh, wait. Dude, I remember those. Like HCl, right? And then you do it with your thing. Alright, anyways. So, yeah, I do remember this from P1. We did discuss this a bit, talking about having yourself, I think this would be a nucleophile or something, and you would have your alkene with a double bond, and the double bond would break, and you would have some substitution going on. I forgot what the name of these terms were, but hopefully we'll learn them. So this is one way. Can be made using this reaction over here, but they are more commonly made by replacing the negative OH group in an alcohol. So your alcohol is an alkane with an OH group at the end, right? So breaking that OH group off by a halogen atom. That's the method we'll concentrate on this page. So you have your you have your alcohol group in your alcohol, your OH group in your alcohol, and you're gonna go and break that. You're gonna remove that and replace it with your halide, just your halide, so your X. Okay, now making halogens from alcohols using hydrogen halides. This is the first method. Your ROH. Yeah, we're not talking about. Whoa. Okay, we're talking about the second method actually. Oops. And the first thing we're talking, and instead of they mentioned halogen atom, so that could be a hydrogen halide. In this case, we're going to be talking about the halogen atom as being a hydrogen halide. So we would have ROH plus HX. Now ROH, R is going to be obviously your alkyl group. Doesn't matter how long the OH is, just matters where that OH is, and we're going to be attacking that one position. HX is going to be your hydrogen halide. It's just your H times your R thing. As a product, you'll get your R with bonded by your X, and the OH and the H form an H2O. Now making your chloroalkanes. Chloroalkanes is going to be this thing, right? This thing, if R was your if your X was your chlorine, if the halide being used is chlorine. Okay. Possibly make chloroalkanes successfully from the corresponding alcohol and concentrated hydrochloric acid. So, what are they saying here? You can make tertiary chloroalkanes from corresponding alcohol and concentrated hydrochloric acid. Hydrochloric acid will contain HCl, which is basically your hydrogen halide. But to make primary and secondary ones, you really need to use a different method. The reaction rates are too slow. So for some reason, the reaction rates are too slow here, but the reaction rates are fine enough in tertiary chloroalkanes. Now, as you remember, these are too slow probably because these are too hard to break. Yet tertiary chloroalkanes are the easiest to break. They have the lowest boiling point, so the reaction will be the greatest, so the reaction speed will be the greatest. So these ones are the only viable ones, tertiary chloroalkanes. But in case you wanted to make primary and secondary ones, say primary is the nicest looking ones, right? It has the Cl at the end, and it has all the C's in the middle and whatnot. So if you wanted this, and maybe personally perhaps you wanted one with a straight chain, so you wanted greater dispersion forces, and whatnot. However, this straight chain one already has dispersion forces that you need to break it, and so no, wait, is that what we're talking about? Because the reason I'm confused here is because since we're reacting and we're not dissolving, so we're only talking about the carbon fluorine bond here. Carbon. Hold on. This is your alkane. Why is it too difficult? Well, as we know, the primary and secondary ones. What was it? Energy released is less than the energy used to break them. I'm not exactly sure actually. My understanding is that, okay, let's just quickly read through above, because this is actually kind of important. So when you have the boiling points of these isomers, right, you're saying that the temporary dipoles are the greatest for the longest molecule. So it's hardest to break the temporary dipoles on the longest on the straight chain molecule, but it is easier to break the thing on one of the branches. If it's already a branched alkane, and you're breaking one of the hydrogens off of one of the branches, then it's much easier because the boiling point, the all the attractions that are present in that alkane are weaker already, so the reaction rate would be quicker. Anyways, tertiary chloroalkane can be made by shaking the corresponding alcohol with concentrated hydrochloric acid. You have your alcohol, you have your concentrated hydrochloric acid at room temperature. Those are going to be that's going to be your tertiary with your OH, CH3, CH3, and CH3. Now this could have been however long as we wanted. The only point is that being this C needs to be bonded to 3 other things, including that O. So when you bring in that Cl and it binds, we get that CCl bond, and that C is bonded to 3 other things, making it a tertiary bond. And then that OH attaches with the hydrogen, Cl attaches with the C, substitution, bang, and you get your CCl and your H2O. Now, if you want bromoalkanes, okay, so now we're switching from chlorine to bromine, rather than using hydrobromic acid, which sounds hilarious by the way, but you usually treat the alcohol with a mixture of sodium or potassium bromide, okay, and then concentrated sulfuric acid, okay. This produces hydrogen bromide, which reacts with alcohol. So you're having potassium bromide, which is going to be what is that? Potassium bromide. That sounds like you have your metal and you have your halogen. So that sounds like a salt, right? And you're going to mix that with sulfuric acid, which produces hydrogen bromide gas or whatever. Now hydrogen bromide, the hydrogen is coming from the sulfuric acid H2SO4, and so the hydrogen bromide will react with the alcohol, okay. Basically what we're saying is we want hydrogen bromide, because originally we're always talking about hydrogen halide bonding, making bonds with the R, okay, ROH. Now how do we get the HX if the X in this case is going to be bromine? For when it was chlorine, what we did was we just used HCl, which is the easiest form. However, BCl is, for some reason, we don't do that. This could be a star for why. Why are we not doing this? And instead, we use, NABR or KBr, okay, and then react these with H2SO4, H2SO4, and then that forms your BHB, which then will bind with your ROH. Okay. Now, this mixture is warmed to distill off. So after it produces hydrogen bromide. So now the mixture with the hydrogen bromide and the rest will be warmed off to distill off this bromoalkane. Whoops. No, the hydrogen. Okay, so the hydrogen bromide reacts with alcohol, and then the mixture of the bromoalkane will be warmed off so that the bromoalkane itself can get distilled. The practical details of the reaction will be further down the page. Okay, no problem. So simply put, you got your HBr bind with your OH. You get what you need, and you get the H2O, and the mixture is warmed off or something, but that's talked about later. Now, making iodoalkanes. You can imagine the same thing. Here you have, in this case, the alcohol is reacted with a mixture of sodium potassium iodide and a concentrated phosphoric V acid H3PO4. And the iodoalkane is distilled off. The mixture of the iodide and the V produces hydrogen iodide, which reacts. So it's the same story, except just different characters, different actors. Over here, we're having potassium or sodium. So potassium and sodium are still going to be your people who are going to carry your chlorine, your halogen. But the acid changes from the previous one. It was going to be your sulfuric. Now we're talking about concentrated phosphoric, H3PO4, which produces that hydrogen iodide, which then reacts with the alcohol to form iodoalkane. Distilling it off, that's part of the practical, but you need to distill it off. And so then you get H2O and this, which you need. Now phosphoric V acid is used instead of concentrated sulfuric acid. This is a good question. Why are we using phosphoric instead of sulfuric? Because sulfuric oxidizes iodide ions to iodine and hardly produces any hydrogen iodide. Usually, the iodide ions will go straight to iodine and not hydrogen iodide. A similar thing happens to some extent with the bromine ions in the preparation of bromoalkanes, but not enough to get in the way of the main reaction. So this also happens with bromide ions, but not enough. If you're interested in the reaction between halide ions and concentrated sulfuric acid, you can follow this link. This is cool stuff. In the present context, all you would need to do is read the beginning of that page. Do we do it, chat? I'll just read it to you guys. There are two different types of reaction which might go on when concentrated sulfuric acid is added to solid ionic halide like sodium fluoride, chloride, bromide, or iodide. There's two types of reactions. The concentrated sulfuric acid can act as both an acid as and as an oxidizing agent. Now, the concentrated sulfuric acid gives a hydrogen ion to the halide ion to produce a hydrogen halide. Because this is a gas, it is immediately escaping from the system. If the hydrogen halide is exposed to moist air, you will see it as steamy fumes. Okay. As an example, concentrated sulfuric acid reacts with solid sodium chloride to produce hydrogen chloride and sodium hydrogen sulfate. This is hard to visualize, it'll still be fine. That's all we need. I don't think we need to know oxidizing agents, but we'll read it. With fluoride or chloride ions, concentrated sulfuric acid isn't strong enough oxidizing agent to oxidize fluoride or chloride ions. As you remember, we only use sulfuric acid for bromine, but not for fluorine and chlorine, because in those cases, all you get produced are steamy fumes of hydrogen halide, hydrogen fluoride, or hydrogen chloride. Oh, wait, hold on. If you look at our original document, we're using iodo, bromo, chloro. Okay, so the only case where we use phosphoric acid is during your bromo, and you don't use it no. What? Okay, I'm getting confused, and it's not best to do this. It's okay, whatevs. We'll think about this later. Okay, so now you're making halogen alkanes from alcohols using phosphorus halides, bro. I don't care about all this. My days. Okay, fine. Let's go through this. So you're making halogen alkanes from alcohols using phosphorus. So you're still making it from the OH groups of that alcohol chain, but now instead of using your hydrogen halides, now you're using phosphorus halides. Okay, that's gonna be your PCl3, right? Chloralkanes can be made we're going straight into it. Talking about chlorine now. Chlorine can be used by reacting an alcohol with liquid phosphorus chloride, PCl3. You have your 3 Cl atoms. The reason for choosing a slightly bigger alcohol as an example rather than using ethanol is that chloroethane, which would be formed with ethanol, is a gas. So see, first of all, why are we making up this problem in the first place? Because when you have a slightly bigger alcohol, then you're gonna have it's gonna be harder to break, right? So it's gonna be harder to react. The reason why we're using a slightly bigger one is because rather than using ethanol, which is the smallest one, is that chloroethane, which would have been formed with ethanol, is a gas, and the preparation would have to be handled differently. Chloro-1-propane is liquid. Basically, when it's chloroethane, the boiling point is so low, it is reactive, but as a result, the boiling point is so low that it's a gas, so the experiment has to be handled differently. We want the product always to be a liquid, so we can make it like there is one concrete method of doing it. So in this case, we use a bigger atom which has bigger attractions, so it has a larger boiling point, so it's not a liquid when it's created. So it's not a gas when created. They can also be made by adding solid phosphoric V chloride, PCl5, to an alcohol. So we talked about PCl3, and also now we're talking about PCl5. These are the two reactants that we can use reacting with alcohol. This reaction is violent at room temperature, producing clouds of hydrogen chloride gas. It isn't a good choice. So it does form a HX. It does form a hydrogen halide, but it's not a good choice as a way of making haloalkanes, although it is used for the test for minus OH groups, negative OH groups in organic chemistry. So the only use being here as a test for OH groups in organic chemistry. Other than that, it's not good because it just produces clouds of it, and that's just not good. There's also side reactions involving POCl3 reacting with alcohol. We're not going to be talking about them, but POCl3 is another one that we can be thinking about. There's side reactions involving it. Making bromoalkanes and iodoalkanes. So again, using phosphorus halides. Now we want to be thinking about bromo and iodo. Now again, bromine and iodine reacting with alcohol. So these are both made in the same general way. Instead of using phosphorus, bromide, or iodide, in the previous case we used phosphorus chloride. In this case, we're going to use the alcohol is heated under a reflux with a mixture of red phosphorus and either bromine or iodine. Okay, a lot weird term here for reflux, but you can think of it as like a little item. We'll talk. I'm hoping that we're going to be learning about what that is when we do the practical. But the alcohol is first heated under a reflux with the mixture of red phosphorus and either bromine or iodine. So you're gonna have that reflux thing. You're gonna put in that alcohol and you're gonna heat it with a mixture of red phosphorus. So you're gonna have in here, you're gonna have your alcohol. You're gonna have your red phosphorus plus like this is gonna be a mix, and it's gonna be red phosphorus plus your bromine or iodine, BRI. Okay, BRI. These are going to be the two things that's going to be inside your reflux as they get heated. Now, the phosphorus first reacts with the bromine. Okay, the mixture, the phosphorus reacts with the bromine or iodine to get phosphorus halide. You're going to get your halide that you need, the phosphorus halide that you need. Then these react with the alcohol to produce or to give the corresponding halogen alkane, which can be distilled off. So as we know, this reacts with this to form your very nice halogen alkane, and as a product, as you get this every single time. Okay. Making bromethane in the lab. So now this is an example. This is a simple example of organic preparation and is one of the most commonly used in A-level chemistry courses. The method described below is not complete. It deliberately avoids mentioning quantities and doesn't cover any of the safety aspects. You can find details in most organic practical books. Perhaps we will be going into that later. I don't think it will be in this video, unfortunately. So I don't know. Anyways. Again, I just want to make sure you understand that the byproduct of these will always be H3PO3. Okay. Now, we're going to be making bromoethane. So you're going to be making bromoethane. And if you want to be making bromoethane, first of all, note we're using ethane. That's the smallest one. We're using bromine. Oh, excuse me. And how are we going to be doing that? So, since it's bromine, so are we using phosphorus or are we using sulfuric? In this case, we're talking about sulfuric. Hold on. I am a bit... So over here, we're talking about phosphorus halides, and the other one, we're talking about hydrogen halides. Okay? And when we're talking about hydrogen halides, we noticed that chloro used, let's highlight these. So chloro used concentrated hydrochloric acid. Okay, bromoalkanes used sodium potassium bromide, concentrated sulfuric acid, and iodoalkanes used concentrated phosphoric V acid. Okay. And again, this one uses two things. You can have phosphoric 3 chloride or solid phosphorus V chloride, and also POCl3. And then for bromoalkanes and iodoalkanes, you're gonna have your alcohol, your red phosphorus mixed with one of the two, and you're going to react those both in a heating reflux, and you're going to get, yeah, you're just going to get your thing. There's going to be no hydrogen halides involved here. However, in this other one, hydrogen halide was involved. In this, your hydrogen halide was involved. We're going to change this color a little bit for now. Your hydrogen halide was involved over here, but that was only when talking about your solid V chloride, solid phosphorus chloride. Now going back into it, if we're using bromoethane, or if we're trying to make bromethane, then we need bromine. And if we have bromine, then we can either go one way using phosphoric, red phosphorus, plus your, red phosphorus plus your, your bromine, plus your alkane, alcohol, inside your reflux and heat it. Or you could go the other way. Can you use, what was the two things? It was bromine or fluorine? No, bromine or iodine. Those are the only two ones. You can imagine them as the ones on the bottom as you go up a little bit. Not so bromine and and iodine. Not, this is iodine. This is bromine. Not chlorine. Not fluorine. Okay. Now, so you could either do it like this way, or you could do it the other way, which is literally just, sulfuric plus your potassium or your sodium, bromine, giving you the hydrogen halide, plus your alcohol, giving you what you need, which is going to be your H2O plus your hydrogen haloalkane. Now in this case, we're starting off with this concentrated sulfuric acid, slowly added and shaken. Okay, so keywords here, let's just mark it down. Concentrated sulfuric acid, this is the way we're going. So we're immediately going with method number 2. It's added slowly with lots of shaking and cooling to some ethanol in a flask. Ethanol in a flask. Ethanol is going to be your alcohol in this case. Care has to be taken because a great deal of heat is produced when the two are being mixed, and there's a real risk of that ethanol boiling and spraying concentrated sulfuric acid around. Solid potassium bromide is then added to the mixture, and the flask is connected to a condenser so that the bromoethane form can be distilled off. Okay, so things that need to be noted over here. First of all, you're adding the concentrated sulfuric acid in with the ethanol in a flask by shaking it and adding it slowly and cooling it as well. So you're doing two things. You're doing one shaking. Sorry, you're doing one adding it slowly. You're shaking and you're adding cooling. Okay, and the first step is really putting that concentrated sulfuric acid into that ethanol in the flask. Then, step number 2 is then put in the sodium, solid potassium bromide. This could also be sodium bromide, into the mixture, and the flask is connected to the condenser. So this is another step, that it's connected to the condenser so that the bromoethane form can be immediately distilled off. Why does it need to be distilled off? I'm not sure. So you have your KBr, HBr, KBr forming the HBr forming the hydrogen alkane. Bromoethane has a low boiling point but is denser than water and is almost insoluble, and to prevent it from evaporating it is collected underwater in a flask surrounded by ice. Sometimes it is simply collected in a tube surrounded by ice without any water. So you don't want it to be gas because that has a low boiling point. But since it's denser than water, you can put it under. You can put it under water surrounded by ice, and it'll just stay there, I suppose, as liquid. But the reaction is heated gently until no more droplets of bromoethane collected. So this is the last step. You just continue heating the reaction flask until no more droplets of bromoethane collect. Now, purifying the bromoethane. So now you're gonna have impurities in the bromoethane, including, which include hydrogen bromide. So you're gonna have unreacted your unreacted hydrogen halide. You're gonna have some pure bromine. You're gonna have sulfur dioxide, which is formed from when the sulfuric acid oxidizes the bromine. Unreacted ethanol, uh, ethoxyethane. Now, before we continue, let's talk about from where these are formed. So hydrogen bromide, although most of it will dissolve, you're still collecting bromoethane. Although most of that will dissolve in the water if you're collecting the bromoethane underwater. So if you're collecting it underwater, most of it you're going to be collecting. However, some are going to get excluded. Bromine, again, as we talked about, it's from the oxidation of bromine ions by the concentrated sulfuric acid. Some of it is going to be turned into it, as we learned that one note. Sulfur dioxide is formed when concentrated sulfuric acid oxidizes the bromine ions. So again, we're talking about sulfuric acid and bromine ions, so you're going to get sulfur dioxide. Unreacted ethanol and ethoxyethane diethyl ether formed by a side reaction between ethanol and concentrate. So this is another reaction between pure ethanol and sulfuric acid. Pure ethanol and sulfuric acid. Okay. So this would happen usually at the start. Like we call this S. This is just unreacted, but this would be S. S to be the start of the reaction where you put those two together in that flask and heat it slowly, or whatnot. Sulfur dioxide. So you're gonna have your, sulfur. Like, see, the sulfur is not supposed to react with the ethanol. However, it will, and whatnot. The purification process. So how do we purify it? So you're gonna have to collect the bromoethane underwater and transfer the contents of the collection flask into a separate funnel, into a separating funnel. Otherwise, for the impure bromoethane, so if you have collected it underwater, then do that. Otherwise, pour that impure bromoethane into the separating funnel and add some water and shake it. So we have two situations: if it's collected underwater, if it's not collected underwater. If it is collected underwater, then make sure you transfer the contents into a separating funnel, or else just pour the impure stuff into the separating funnel, add some water and just shake it. Okay, pour off and keep the bromoethane layer. So you're gonna have your aqueous layer, you're gonna have your bromoethane layer. So you want to run off the so basically so what's going to be denser is the bromoethane layer. So you're going to let these go down and kind of keep this shut when the aqueous layer comes in. Okay. Now the water you discard will contain almost all of the hydrogen bromide and quite a lot of any bromine, sulfur dioxide, and ethanol is present as impurities. So this is still extremely hazardous. You want to take care of these properly. Okay. And we're talking about the water that we're discarding is obviously this water, okay? And these impurities are again talked about as we talked about it above. Now stage 2, to get rid of any of the remaining acidic impurities, including bromine and sulfuric dioxide. So after we've filtered it out, now you're going to have bromine and sulfur dioxide impurities within your bromoalkane. So return the your bromoethane specifically. So then return the bromoethane to the separating funnel and shake it with either sodium carbonate or sodium hydrogen carbonate solution. So we're going to go back to another separating funnel. Okay, and again, the new acidic or like the acidic impurities that's going to stay are going to be your bromine and your sulfur dioxide. So you want to go back into the return the bromoethane back into the separating funnel, shake it not with water but this time with sodium carbonate or sodium hydrogen carbonate solution. Now this reacts with any acids present, liberating carbon dioxide and forming soluble salts. So the impurities present will react, which liberates the carbon dioxide and forms soluble salts. Then you simply separate and retain the lower bromomethane layer as before. So you do the same thing, right? And you'll have the carbon dioxide and you'll have your salts maybe at the top, and you'll have like the bottom layer, which is going to be your bromomethane layer. Now you want to filter that, and then you want to wash the bromomethane with water in a separating funnel. So again, take these out, get these out, then you want to put these in a funnel, another separating funnel, and then you want to remove any of the inorganic impurities, which is excess sodium carbonate solution, which is going to be sodium carbonate solution from the thing above here. So you want to remove that. So you put in something to remove impurities, but then now the thing that you used to remove the impurities is now an impurity. So now this time you want to transfer the lower bromomethane layer to a dry test tube. Okay. So two things. You want to wash the bromomethane with water inside another so you want to put it back into a separating funnel, put some bromomethane, wash it with water to remove any remaining, and then this time, oh wait, okay, so this was used to remove the inorganic things. So this time the inorganic would be sodium bicarbonate solution, etc. And then this time you want to transfer the lower thing into a dry test tube. In that dry test tube. So finally, when you have this, you're gonna have this containing your water plus the inorganic impurities, II, and your bottom one is gonna be your bromomethane layer. You want to move the bromomethane layer into a dry test tube. Okay. Add some anhydrous calcium chloride to the tube. So into the tube you want to add anhydrous calcium chloride. It's going to be like a salt. Shake well and leave to stand. The anhydrous calcium chloride is a drying agent and removes any remaining water. It also absorbs ethanol, and so any remaining ethanol may be removed as well, depending on how much calcium chloride you use. So it removes impurities such as the remaining water. It also removes any other impurities such as ethanol. Specifically ethanol it removes as well. And this happens because it's a drying agent. Now stage 5, you're going to transfer that new dry bromomethane into a distillation flask and fractionally distill it. Holy shit, bro. That is insane. So sorry, I got distracted by like this bottom part. Anyways, so transfer the dry bromomethane. So now the bromomethane is now dry. So you want to put that into a distillation flask and fractionally distill it. As you remember, fractional distillation was like you got the layers and like it'll go up depending on the boiling point. So collect what it distills over between the 35 and 40 degree marker. So let's say this was 35 and 40 degrees. So everything that collects over here, you want to collect that. In principle, they should remove any remaining organic impurities. In practice, though, any ethoxyethane, which is perhaps the most likely impurity left, has a boiling point very, very close to bromethane, so it is unlikely that you will be able to separate the two. If there is any ethanol left, which hadn't been absorbed, then it would certainly be removed because the boiling point is much, much higher. Okay? So, since the boiling point is much, much higher, it would be somewhere much, much lower, so it would be collected here. We're collecting anything here. The most likely thing to be the most likely impurity is going to be your ethoxyethane now. Again, collect between 35 and 40 and fractionally distill it. Move it to so you want to move it, 1 distillation flask, 2 fractionally distillated. The most common impurity at this stage will be ethoxyethane, but it is unlikely to separate those two because they have similar boiling point. But definitely any of the ethanol left would be removed. What's left, in my experience with A-level students, virtually nothing. If you're working on a small scale, every time you go through a purification stage, you will inevitably lose some of what you were trying to collect. We're done here. Okay, next chapter. reactions between halogen alkanes and hydroxide ions. So what we did before here was going to be your reactions in general. These are going to be just your common reactions with your, oh sorry, whoops, you're making, so the reactions involved in making your halogen alkanes from alcohols. We didn't talk about alkanes here. Alkenes would probably be talked about last year, so if you want to learn about that, then you want to go back a year. No, sorry, back a unit. You know, so yeah, that's pretty much it for this. Now we're going to more specific reactions between halogen alkanes and hydroxide ions. Okay, so listening to what they have to say before maybe perhaps a small break, is this page looks at the reaction between halogen alkanes, haloalkanes or alkyl halides, and hydroxide ions from sodium or potassium hydroxide solution. I went too fast. Am I recording? Okay, yeah. So, page looks at reactions between halogen alkanes, that's going to be your first reaction, and hydroxide ions, it's going to be your second one, which are coming from sodium or potassium hydroxide solution. Okay, so straight up, first one halogen alkanes, second one hydroxide ions, and that hydroxide ions, it's originating from sodium, potassium, and hydroxide solution. It covers both the substitution and the elimination reactions. Perfection. To a large extent, this page simply brings together information from a number of other pages on the site. If you want information about these mechanisms for these reactions, you will find them elsewhere. What? No. This page goes to other pages, dog. Oh, hell no. To a large extent, this page simply brings together. If you want information about the mechanisms, you will find them elsewhere. This page has links to all the other pages. Bruh. Okay, fine. What else? This is making me very sad, so we're gonna have a... Wait, hold on. Yeah, I'm really sad about this information, so we are not crying. Substitution elimination. There are two different sorts of reactions that you can get depending on the conditions used and the type of halogen alkane. So there's going to be two types of reactions, and it depends on, so that's going to be your dependent variable. Your independent variable in this case is going to be the conditions, and so that's going to be one is going to be your conditions, or we can do it, A is going to be your conditions and B is going to be the type of halogen alkane. Again, primary, secondary, and tertiary. So remember, when we first began learning about primary, secondary, tertiary, we said that it would have different chemical properties. So different chemical reactions would happen due to those different chemical properties. So in this case, we're going to see that when these, substitution elimination reactions, substitution and elimination are the two types of reactions, right? So it depends on, so you can either result in a substitution or elimination due to the conditions and also due to the type. So for your substitution reactions, the halogen atom is replaced by an OH group to give an alcohol. Simple enough. You have your NaOH, you have your Br. Wait, what? Oh, bruh. Okay, bruh. Halogen atom is replaced by an OH group. Okay, so before we were replacing an OH with a halogen, now we're pursuing a bromine, a halogen with an OH. Okay, so this is a pretty big distinction to make. When we were talking about making these little boys, HXs, we were actually removing the OH groups. Now if you want to, now we're learning about the reactions, and we're actually removing the X from the C, using the OH. So it's like the OH is like revenge. So the OH, that's like. So. It's evil. Like. And he's coming in with his like steed, and his steed is gonna be literally like a horse or like a wolf, and the wolf's name is literally sodium hydroxide. Okay, we're done with that. So yeah, for example, you're gonna have this, and check a look at the products. You're gonna have NABRs as your side product, and your main product is obviously gonna be your OH. So BR is gonna react with Na, forming that thingy. Or as an ionic equation, so we're checking this out as an ionic equation. Your OH is going to be your negative. Yeah, so this is in reality, this is the most important one that we're going to be looking at. OH is going to be a negative over here, because again, this is a polar bond. This is going to be your positive. This is going to be your negative. So this is going to be negative, and it's going to go to the BR. BR is going to turn into a negative. That is a negative, right? I believe that is going to be a negative over there, negative charge. So it forms a negative with NABR, because again, NABR is going to be your very polar molecule. If it was iodine, that would not form a polar molecule. I don't think so. Unless it was given an electron, extra electrons, then it would be a different story. Now in this example, 2-bromopropane is converted to propane 2-ol. Are you seeing that? 2-bromopropane, propan 2-ol. Yep. The halogen alkane is heated under the reflex. So again, we're talking about reflex heating. So the halogen alkane is heated using the reflex with a solution of sodium potassium hydroxide. Last time we were talking about reflex, it was red potassium plus your alcohol plus the red potassium would be in a mixture with your sodium iodine or bromine. In this case, if you want your halogen to be switched out, you want to heat the halogen under the reflex with the solution of sodium or potassium hydroxide. Okay, and heating under reflex means, why are we heating under reflex? Because it means that when you heat with it, a condenser placed vertically in the flask prevents the loss of volatile substances from the mixture. That's the entire point of this. You're heating it under a reflex so that the products that are formed, such as the volatile substances like NABR, is not lost, because that would be lost as a gas. The solvent is usually a 50-50% mixture of ethanol and water. Yeah, you would have ethanol, but you would also have water, because everything would dissolve in that. The halogen alkane is insoluble in water. Of course, if you use water alone as a solvent, the halogen alkane and sodium hydroxide wouldn't mix. Okay, we're back. It's been a while. It's definitely been a while. Alright, so talking about substitution reactions. It's gonna take me a bit to recollect myself, but it's okay. Substitution reaction. Yeah, so we have a halogen alkane that's heated under a reflex with a solution of sodium potassium hydroxide, heating under a solution. So why are we heating it under a reflex? We're heating under a reflex because it means that heating of the condenser, because it means that we'll be heating it with a condenser that's placed vertically in the flask, so that we can prevent a loss of a lot. Now the solvent itself that we use is what solvent are we talking about here? The solvent is usually 50-50 mixture of ethanol and water. So the solvent that's made as a product because the mixture is going to be your thing. Okay, so what I'm guessing is it's going to be this, right? So since the mixture was containing this, and then you get this OH at the end of it, right? So you get this alcohol at the end of it. So this alcohol will be with the remaining water that's produced from the condenser or whatnot. And everything can dissolve in that. Haloalkane is insoluble in water, so it is originally not dissolved in the water. If we use the water alone as the solvent, the haloalkane and sodium hydroxide solution wouldn't mix, and the reaction could only happen where the two layers met. So we dissolve this entire thing in the solvent. How then? Or something. Okay, perhaps we need to follow up on this. So if you click on this, no, let's see. Yep, we definitely have to be talking about this first. So if we print this, hold on. Let's see. So this is kind of like talking about the practical stuff. I'm not very 100% on this. What mixture are they talking about here? I have no idea. But that mixture is going to be the solvent that the haloalkane is going to be dissolved in. And the solvent contains both ethanol and water. So you have an organic compound plus water. And in organic compounds it reacts more, or it dissolves more, and in water it dissolves less. So since the we need water basically, okay, but if we use water alone as the solvent, the haloalkane wouldn't mix with the sodium hydroxide solution. Now the question is, where is the sodium hydroxide solution coming from? The sodium hydroxide solution is coming from the NaOH over here. See, look, you're gonna have the haloalkane and you're gonna have the sodium hydroxide, and they're gonna be both reacted in solvent. Now that solvent, usually it would be just water, okay? But water wouldn't work because this is absolutely insoluble in water. So if it was there in water, then they wouldn't mix and the reaction wouldn't happen because there would be two layers, one with the NaOH and one with the there would be multiple layers, but there would be one with the NaOH, there would be water, and then there would be one with the haloalkane. And only when these two layers would touch, then the actual reaction would occur. So therefore we don't use a solvent of water, we use a solvent of water plus ethanol, which will give us a solvent that's soluble enough that this the haloalkane is soluble enough within this new solvent of water plus ethane that the reaction can occur. Okay, now we want to learn a bit about the substitution reaction because that is quite important. So we'll open this, and this is quite long. Just going through this real quick. So if you talk about elimination, then we have the mechanism for elimination. Let me just open this. Alright, so there's going to be the 2. After that, just seeing if there's any more. Okay, there isn't. Okay, perfect. So there's the mechanisms. Now mechanisms are important. They for sure are important. However, do we need to study them right now? Because this will take a bunch of time. Because see, as far as understanding goes, mechanism isn't there. Mechanism is just for practical understanding. The actual concept understanding, we do not need mechanisms. Mechanisms wouldn't change how we understand it. Or perhaps it would. I'm just saying this because I don't want to spend so much time on it, but I suppose we could do it. If you aren't sure about the differences, okay. No. I'm not happy about this, but it's okay. The halogen alkane is heated under reflux with a solution of potassium hydroxide. The halogen replaced by the OH is the halogen will be replaced by the OH. Yep, this is exactly what we studied. Now, heating under reflux, the reason we do this again is that there's a condenser plate vertically in the flask that prevents the loss of volatile solvent. This is a repeat. Now, we have a first example. We're using one bromopropane, so it's bonded at the 1, and this is a primary. So this is primary halogen alkane. We're using one bromopropane, and we do it, and we get this. We get the OH, which is the alcohol, and we get Br minus. We could write the full equation rather than the ionic one, but it slightly obscures what's going on. Same thing, Br, and we have NaOH. OH is the negative, Na is the plus. Over here, Na is the plus, Br is the minus. Okay. In other words, the bromine or other halogen, that halogen alkane, is simply replaced by an OH group. It's just simply like that. The halogen is replaced by the OH group, and it could be any other halogen, hence a substitution reaction. In this example, propan 1-ol is formed. As you know, there's 1, 2, 3. So there's ethane, methane, butane, ethane, methane, propane, butane. Oh no, I forgot the names. My bad. And that's propan 1-ol because the one is the first one. Over here. And the mechanism. So we're saying the mechanism involving bromethane. This is an example of nucleophilic. Please do not forget the names. This is very important. Okay, this super important. Okay. Now, just look at what's going on here. Actually, I think they're gonna explain to you what's going on. Okay. Oh yes, SN2. This is my class just talked about this. So what we're having is we have CH2. This music is so loud. Relax. Okay, so you have your OH minus and your CH2 plus, and your Br minus. So this is gonna be your so your CBr bond. H, I would like to prefer writing it like this. Just if you wrote it like this, right? And it's your that's why the delta positive is on top of the C, right? So you're gonna have your your C and your Br and your OH negative, okay? And so it comes in, and it's gonna be the fission is going to be heterolytic, so both electrons in here are gonna go to the Br. So then as a product you'll have Br, and it's going to be negative charged because again it has extra electrons, and it was delta negative, but it was still neutral here. So now it becomes negatively charged with these extra electrons, and this was negatively charged with the extra electrons, but now it's moved in, uses those two extra electrons to form the bond with the CH2, and now it's neutral. So now we have 1, 2, so this is going to be ethane, methane. This is going to be methyl 1-ol or methane 1-ol or something, plus your bromine ion. Okay. Now this is an example of nucleophilic substitution. Because the mechanism involves the collision between two species in the slow step, in this case the only step of the reaction, it is known as an SN2 reaction. So SN2, so since it requires only two species in the first step, okay, or in the slow step, then it's known as SN2 reaction. Okay, so two species, and it's a nucleophilic substitution. Perhaps that's what it means. Now, if your examiners want you to show the transition state, draw the mechanism like this. So, as we know, your OH goes into the C, which is positively charged, and it shows the 2. So then this goes to the Br, this goes to the C, so yeah. And then you'll form C with 5, which is going to be your OH, your Br, the H, the CH3, and your H. So your 2 H's, your OH, and the next CH3, and then your Br. That's going to be a transition state where the entire thing is negatively charged, and then it's going to go into that. So now you're going to have the next reaction, which is the reaction of tertiary halogen alkanes. So this was going to be your primary. Now you're going to have your tertiary with the hydroxide ions, and it's going to change slightly. We also studied this in my class. So the facts of the reaction is that it's exactly the same. However, if the halogen alkane is heated under this, then if the halogen alkane is heated under reflux with a solution of sodium or potassium hydroxide in a mixture of ethanol plus water, then the halogen is replaced by OH and an alcohol is produced. Is that exactly the same? That's exactly the same. CH3CBr, OH, and then you're gonna have that. And if you want the full equation, you're gonna have CH3CBr and OH. Now, what this means is CH3CBr is gonna have your C, you have your Br bonded to 3 other CH3s. Okay. So when the OH, when you break this, or well, at least when you have the Br, then you're gonna have the C that it's bonded to 3 other things. Okay, clean. The OH bonds to the exact same area, and your Br that comes out is going to be negative, so it's exactly the same. The mechanism involves initial ionization of the halogen alkane. So first in the slow step, you're going to have Br, which turns into this, and this has a left over positive charge, followed by a very rapid attack of the hydroxide ion on the carbocation. So OH is already existing as this. However, where does OH form? It forms from the H2O, right? So you have, and then you have this thing. You could have like possibly this going like this. So this has 2 electrons, so electrophilic substitution. So then you leave H as a plus and you take OH, the whole thing with 2 electrons as a negative, and now you have it this, and it goes into this, and it goes quickly into this whole product. Okay, so this is an example of nucleophilic substitution. We'll mark it down again because I really need you to remember this point. This time we show a slow step of the reaction which only involves one species. So now it's SN1. So we have nucleophilic substitution probably for S, or maybe S stands for species. I'm not sure. I would say SN, which is like substitution. It's nucleophilic with a one species in the slow step. So remember, in the slow step, you need this to be, and perhaps if you want to generate a reason why initial ionization has to be like this for tertiary, you could think of it as perhaps, see, when you have this, okay, you break the bond by using the OH negative's charge to repel the electrons back into Br, okay? But over here, this could be possibly wrong, but this is how I'm kind of visualizing it. Whereas over here, this is so weak that it happens on its own. Okay, that it happens on its own because the boiling point is so weak because it's a triple bond. So your what's called your attractions. What's it called? The dithering. I forgot it, bruh. Are you kidding me? It's embarrassing. Like your dispersion. Okay, my fault. So your dispersion forces are much weaker, so then it just breaks on its own. That's going to be your slow step. And so then you form this, and of course this is equilibrium, so this could actually just go back into it. Okay, and so as a result, then you'll have this, and in the fast step you'll form your actual product. And lastly, the reaction of secondary. This is going to be exactly the same as primary or tertiary. The halogen alkane is heated. Okay, see, they are making this a very big point. The halogen alkane will be heated under a reflux with the solution of sodium or potassium hydroxide in a mixture. So again, look, they said at the start that your conditions and your type of halogen alkane is going to matter. So that's why they're stating the conditions every single time. Okay, So in this case, you're going to have Br in the middle, and you're going to see that the C in this case is bonded to one and another CH3. Okay, the alkyl group that Br is bonded to two other things. So you're going to have one OH negative coming at you. There is for some reason they didn't draw the two electrons over here. Is that only for? I'm actually not quite sure why they didn't do that. That's actually a star, because I do want to understand if there is something important behind that. Oh, this is just the general. Oh, oops. Okay, this is just the general. Okay, whoops. Okay. Now the actual mechanism is yeah, this is definitely not the mechanism. This is the mechanism where you have your OH, and again, we're using the terms SN2 and SN1 in this case. Okay, it uses both, for example, so it can go both ways. Okay, and so in the SN2 mechanism case, it goes. You have two species here, so you have your Br going away and your OH coming in, and you get the products. And over here, should you need it, the SN1 would have two stages where the Br goes away. And so you can imagine that, in primary, it's so strong that you only need SN2, which is this, where they both happen at the same time. Tertiary, which is so weak that you go only SN1. But then secondary is kind of in the middle, so you go SN1 or SN2, depending on what you need. So the SN1 mechanism would be, again, your Br wicks first, and you have your positive point and you have your negative, and then OH comes in and you get your fast point. Now there's another reaction involving halogen alkanes and hydroxide ions involving an elimination reaction. So yes, we need to go through that as well. However, let's continue a bit. So halogen alkanes also undergo elimination reactions in the presence of sodium and potassium hydroxide. So the reactants are same. Okay, the 2-bromopropane has reacted to give an alkene. Okay, so elimination forms an alkene. Interesting. What is going on here? First of all, before we go into this, note what they said before. There's two different sorts of reactions that you can get depending on the conditions used and the type of halogen alkane. So A and B, either the conditions used and the type of halogen alkane. And there's two different sorts of reaction, which is substitution or elimination. So over here, 2-bromopropane has reacted to give an alkene propane. Of course, this is going to be hard to visualize when you can't see the mechanism. Notice that the hydrogen atom has been removed from one of the carbon ends. So you're going to have CH2CH. So since it's a double bond, this is 1 to 1 and this is 2 bonds, and so we can't have that extra hydrogen. So one hydrogen has to go to H. Okay, so then one hydrogen has been removed together with the bromine. Bromine is also removed from the center one. In all simple elimination reactions, the thing being removed are on adjacent carbon atoms, and a double bond is set up between those carbon atoms. What they're saying is, when you originally you had what? You had right? So we're having CH. These are all H's. So it's like, yeah. So now when the well, I'm not even sure how this works, but the Br left formed the double bond, and so as a result, one of these has to go as well. So this will also go, and since and again, what they're saying is the being removed are on adjacent carbon atoms. So these are on adjacent carbon atoms. H and Br are on the adjacent carbon atoms. The halogen alkane is heated under reflux with concentrated solution. Yep, propene is formed. So again, conditions are the same as usual. And this time, remember, your your thing is gonna be ethanol. Okay, that's gonna be your solvent. It's not gonna be water plus ethanol. It's just ethanol. Propene is formed. Yep. And because it's a gas, it passes through the condenser and can be collected. Okay, cool. So propane is gas, so it's collected through the condenser, or rather, it passes through the condenser and it gets collected. Now, over here, you're gonna have a fact, simple, uncluttered mechanism for elimination reaction between simple halogen alkane like 2-bromopropane and hydroxide ions. So yeah, you have a secondary in that case, or is that a 2-bromopropane? Is that 2-bromopropane over here? Rather over here. Yes, or in this case, it's a secondary. So yep, that's a secondary, and hydroxide ions. Yep, the OH minus, and from for example, sodium hydroxide, the negative OH ions will come from to give an alkene like propane. So it produces an alkene like propane. If you want the mechanism, there's a link at the bottom. I think that's the one that we are doing. Actually, I'm not sure. You'll also find a link on the page on elimination from more complicated halogen alkanes where more than one product may be formed. Exam questions on this topic frequently ask about another possibility in the reactions between halogen alkanes, hydroxide ions, nucleophilic substitution. Okay, so this is where exams usually ask whether it'll be nucleophilic substitution or elimination. Is it elimination substitution or just eliminate? Okay, it's just elimination reaction. Okay. So yeah, it's asked. So there's a chance between those two. However, there is still a more detailed explanation of the mechanism and also another elimination reaction where you have more complicated halogen alkanes. If that talks about more than one halogen, I don't know if I should be doing that. And then there's more than one product being formed. So elimination reaction involving 2-bromopropane. So we've already done this. We've already looked at this. So we can go straight to the mechanism. Everything else present, including anything, will be trapped inside the flask. So other than your propene gas, everything else will be trapped. Okay, because the propene gas is the only gas that goes to the condenser. Now the mechanism. In elimination reactions, hydroxide ion acts as a base. Okay, removing hydrogen as a hydrogen ion from the carbon atom next door. So again, reading that carefully, the OH ion acts as a base and it removes a hydrogen as a hydrogen ion from the carbon atom next door to the one holding the bromine. So you have a hydrogen next door to the bromine, and it removes that hydrogen. Okay, so it draws a line between these two, forming that bond between these two. Okay, so yeah, okay, that's what's happening. That's it. Okay, that's a lot of links. Okay, so all right, let's see. Well, see, the first point that as I'm downloading these second things, the first question is, what's going on with that hydrogen? Why does it just come out, right? Because there doesn't seem to be any thing that's pushing that hydrogen that's bonded to the carbon out. It seems like a perfectly stable bond. So that's my first doubt. More complicated cases. We could look at this. It seems like seems like fun. Why not? Okay. So let's go. I hope these are the two. Oops. So these are more complicated, but I want to walk through because just in case. Okay, so what is that? Get that out of my screen, thank you. So yeah, explaining it. So this place goes through the elimination mechanism. Elimination involves more complicated halogen alkanes, involving more halogen alkanes, and competition between elimination and substitution. These reactions are dealt with on separate periods. Okay, so there's actually so understanding when one happens compared to the other is another it's another like point of this entire topic. Okay, I believe if you go all the way back and you go down. Oh, will I just scroll back to this? Because that's kind of what it's talking about. 1 second, actually. No, stop. Let's see. Nope, it is a whole different thing. Oh, but I feel... It looks like pretty much the exact same thing as the one in that other document, so it doesn't really matter. Cool. Yeah, cool. Okay, so elimination. Yeah, okay. Elimination. Okay, yep, we're using the same thing. So your OH ion, yeah. So your OH ion has a very strong tendency to combine with another hydrogen ion to make water. In other case, OH ion is a very strong base. So as you know, if you have an H plus ion, which is going to be kind of like an acid, right, and your OH ion, which is kind of like a base, they have a great tendency to combine to create water. Okay, so in this elimination reaction, your hydroxide ion hits one of the hydrogen atoms in the CH3 group and pulls it off. He pulls it off. He literally just pulls it off. This leads to a cascade of electron pair movements, resulting in the formation of a carbon-carbon double bond and the loss of a bromine as Br minus. Okay, so it's a cascade. So first, you start off with, where's my cursor? Okay. So first, you start off with the hydrogen atom getting pulled off. So it gets pulled off into there. Okay. Then after that, immediately, a cascade of electron pair movements causes a double bond to form, which results in the loss of Br as Br minus, because this takes it and just leaves. And yeah, it needs to, because 1-2 bonds are already present. Okay, the complete mechanism is the OH takes one of the hydrogens, but it only needs the hydrogen nucleus, a hydrogen ion. Oh, it needs only the hydrogen ion. So the electrons from the hydrogen, the double bond, the pair of electrons from the hydrogen aren't needed. So that means the 2 electrons which originally joined the hydrogen to the carbon aren't being used anymore. So those 2 electrons go to form a double bond. Bro, that's sick. This approach, the approach of those electrons repels the electrons in the carbon-bromine bond right out onto the bromine, throwing the bromine as a negative ion. This attack could equally well have been in any other order of hydrogens on the left-hand carbon or any on the right-hand one. It just simply depends on what the OH ion hit. Dude, that is so sick. So literally, this hits this. H goes there, but it only has an ion as like an H plus ion. So the 2 goes into here. This goes into here, so the electrons going into here repels these electrons into the bromine, which again repels bromine out. Brother. Alright. That's pretty cool. Taking chemistry further, the mechanism being described here is known as E2 mechanism. The E stands for elimination, and the 2 stands because the initial slow part involves 2 species. Okay, so remember we had S, which is substitution, then N, which is nucleophilic, then the number In this case, we're having E and then just straight up the numbers. We have no types of elimination reaction. There's only one, and then the number of species in this slow step. Now, there's also E1 mechanism, which would apply to tertiary halogen alkanes. Secondary ones would also do it to some extent. No current UK syllabus will ask you about that. Okay. So now talking about elimination for more unsymmetric halogen alkanes. This page looks at elimination from the unsymmetric halogen alkanes such as 2-bromobutane. Now, okay, first of all, let's look at the difference between 2-bromopropane and 2-bromobutane. Okay, so if you look at the original 2-bromobutane, we'll have, this will have 1, 2, 3 atoms plus the Br in the middle, and CH3 is just written as this, but in reality, it's literally just CH. Forget about this line, CH3, CH3, and you have your Br. So it is symmetrical. Now, if you have unsymmetrical, let's say it comes in from either here or it comes in from either here, what's going to happen? This looks at elimination from an unsymmetric point of view. So now, 2-bromobutane is an unsymmetric in the sense that it has CH3 group on one side and CBr on one side of the CBr and CH2, CH3 on the other side. Now, you have to be careful with the compounds like this because of the possibility of forming one elimination product. You have the possibility of forming more than one elimination product depending on where the hydrogen is removed from. See, the basic facts and mechanisms for these two reactions are exactly the same, like 2-bromopropane, but this page only deals with the extra problems created by the possibility of more than one elimination product. So the fact of the matter is it works the exact same way. However, when you have an unsymmetric one, there's going to be more than one elimination product. We're just going to be discussing that. Okay. Now, background to the mechanism. You will remember that elimination happens when a hydroxide ion acts as a base. Yep, it does, and it removes a hydrogen. Yep, and for example, the simple case from 2-bromopropane, which is symmetrical. Going to look at that. Perfect. The hydroxide ion removes a next to carbon bromine bond. Various electron shifts lead to formation of alkane, and with a unsymmetric hydrogen alkane like 2-bromobutane, there are several hydrogens which might possibly get removed. So there's a lot of hydrogen here that could get removed. You need to think about each of these possibilities. Where does the hydrogen get removed from? Well, the hydrogen has to be removed from a carbon that's adjacent, so it needs to be next to the CH bond, CBr bond. If an OH molecule R ion hit one of the hydrogens on the right hand CH3 group in the 2-bromobutane as we've drawn it, then there's nowhere for the reaction to go. Are we talking about one for one that is not adjacent? So in this case, the electron pair movement can't happen because this movement would cost too much energy. To make room for an electron pair to form a double bond between carbons, you would have to expel a hydrogen from CH2, which forms a hydride, which is just way too energetically difficult, and so this reaction doesn't happen. So basically, if OH was put in, it would happen the exact same way. You would put OH, H will get pulled out, so then this electron would go over here, create a double bond. So there's way too much pressure over here, so this electrons go into H, and it comes out as a H negative with 2. However, this is a hydride ion, and it's too energetically difficult, so it doesn't happen. It just doesn't happen. It can hit it, but it won't react. And that leaves the possibility of removing a hydrogen on either the left hand CH3 or the right hand CH2. Okay, so we talked about if it hits this, but now if it hits this, if it hits this, or if it hits this. Now if so either this or this. If it happens on this, it won't happen. Okay. Now if it was removed from the CH3 group, which is on the left, The product is but1ene. Okay, so we'll see. It goes like this. Br is left, and the product will, you'll see that it is on the left side. The bond. You'll have H2O and you have Br on the yeah. Okay, fine. This makes sense. But if it's removed from the CH2 group, then you'll see. Okay, let's see. Again, if it went like this, okay, because now it has the room, it can choose. However, if it goes into here again, it would result in, let's say, H, H, H. It would result in one of these having to become, one of these having to become a hydride ion, which is again impossible. So, you're having, H taken away, electron going to CH double bond, then going to Br, Br leaves, double bond with a C, double bond with a C, H, CH3, H goes. Okay, fine. Now, this product is but2ene. Yep, it's in the middle. So 2, 1, 2, and it's going to be ene, and it's butane 1, 2, 3, 4. Yep. And if you go up, it's going to be but1ene. So that's like 1, 2, 3, 4, and it's all the way in the first one because this is 1 CH2, so 1. Sorry, rather, it's in the one. This is the first one, this is the second one, this is the third one. Whew. I hope that's correct. In fact, the situation is even more complicated than it looks, but because a but2ene exhibits geometric isomerism. Oh shit, because it's in the middle, yeah? Because over here, H and H is the same, but now, shit, okay. Because of the pi bond, you can have rotational thing. So you can get a cis but2ene or trans but2ene, which would look like, yep, they're showing it. So over here, remember, look at the original one over here. You're having a C double bond, your H is on one time and your CH3 is on one end. In this case, you have C on one end connected to connected to a CH3, and you have H on another end, I believe. Or I'm wrong. Your C connected to, no, sorry, this connects to a C, which is connected to one H and one CH3. Okay, if you cut that out. So then you can write it as the CH2s both go on top, cis butene and trans butene, and then you also have your Z and your E. It's just a matter of chance what gets formed. But again, what is cis? What is trans? Cis is same and trans is different, right? Yeah. Yeah, this seems totally understandable to me. Oh my god, okay, that's a lot of text. So now we're talking about what is geometric isomerism, right? So an explanation of the two ways of naming these are compounds. Follow the link in the box. I don't really need that. So geometric isomerism, where you can draw more than one arrangement for the one given. So geometric isomerism is special cases molecules has restricted restricted rotation around one of the bonds. Carbon double bond, carbon bond could only rotate if enough energy is put in to break the pi bond. Effectively, at high temperatures, the CC bond is locked. In the case of but2ene, the two CH3 groups will either be both locked on one side to give cis or Z, or on opposite sides to give trans or E. Now beware, it's easy to miss geometric isomers in an exam. Always draw alkanes with the correct 120 bond angles around the CC bond as shown in the diagrams for the cis and trans. If you take a shortcut and write but2ene as this, then you'll almost certainly miss the fact that cis and trans are possible. This is a rich source of questions in exam. You could easily throw away marks if you miss these possibilities. So as an overall result, you can get, as an overall result of elimination, you can form but1ene as when you when do you do but1ene? When you hit the left, when you hit the CH3, and these two but2enes, one is cis, one is trans, when you hit the CH2. Okay, Now, if you look at the difference, the competition, we are getting through this, guys. We are getting through this. All right. So the factors that decide whether halogen alkanes will undergo elimination or nucleophilic substitution, right? When they react with hydroxide ions from, say, sodium hydroxide or potassium hydroxide. Details are given elsewhere, but whatever. Reactions. So both reactions will follow under literally the same exact conditions as we know. It's under reflux with sodium or potassium hydroxide solution. Of course, the products will be different, but still, for the most part, it's the same. So, nucleophilic substitution, the hydroxide ions are present are good nucleophiles, and one possibility is a replacement of the halogen atom by an OH to give an alcohol via, yep, this is perfect, in the example of 2-bromopropane converted to propane 2-ol. Makes sense. Okay, again, it's 2 because we're in the middle, and this is going to be secondary. Now, hold on. Does the nucleophilic substitution change depending on if it's secondary or primary or tertiary? Yes. Yes. The mechanism changes, but the overall reaction does not change. Yeah, okay. Let's actually, since I've forgotten that, let's actually just write that down real quick. So, you know, yeah. Okay. Elimination. Halogen alkanes undergo elimination reactions in the presence of blah blah blah. 2-bromopropane have produced to give an alkene, and in this case it would be propene. If we're using 2-bromo propane. Yeah. Notice the hydrogen atom has been removed. Am I still like? Is my little guy still talking? Let's go, dude. That's so awesome. Notice that the hydrogen atom has been removed from one of the ends. I'm okay. I'm like actually going crazy. Sorry, I'm losing it. So hydrogen atom has been removed from one of the carbon ends together with the bromine. Bromine is also removed from the center one. In all simple elimination reactions, the things being removed is on adjacent, and the double bond is set up between. Yep. Now, what decides? Finally, we're actually talking about it. That was a good recap, though. So, the regions you're using are the same. Halogen alkanes. Yep. So we'll just mark this again, just to make this very clear. Halogen alkane. All right. There's sodium or potassium hydroxide. You get a mixture of both. In all cases, you'll get a mixture of both reactions happening. Okay. So when you have them, when you put them, since it's it's the marker. Sorry. So when you actually do them, and since they require both of the same conditions, that means in your little, reflex flask or whatever. You're actually going to get a mixture of both. You're going to have substitution and elimination. But what you get most of depends on a number of factors. Okay. This is the most important factor, and it's the type of halogen alkane. Okay. So finally, we'll actually talk about, this is the type of halogen alkane truly does matter. Not only does it change the NS, but it will also factor in whether it will be the NS or if it will be the E. Okay, so primary, secondary, tertiary. Okay, primary is mainly substitution. Secondary is both substitution and elimination. Tertiary is mainly elimination. Think about this before you read. Primary, hardest one to do. Substitution happens in 2 steps. Okay, and that's 2. Secondary, both. Tertiary, easiest one, mainly elimination, because perhaps there's nothing that pushes off the BR in tertiary except for the literal electrons within as the double bond is formed. So perhaps that's why. That would be my understanding. Well, anyways, for example, whatever you do with the tertiary halogen alkanes, you will tend to get the elimination reaction, whereas the primary ones you will tend to get mainly substitution. However, you can influence things to some extent by changing the conditions. So here you have the conditions that you're changing. And the solvent, the temperature, concentration, okay, these 3 things. Okay, first of all, the solvent, remember when we had in this case it would be water 50, ethanol 50. Okay, water encourages substitution, ethanol encourages elimination. Think about it a little bit. Why would that be happening? I couldn't really explain this. Ethanol encourages elimination. Yeah, I have no idea. Higher temperatures encourage elimination. Do I just need to like understand this, or do I just need to like listen to this? Oh my god, these explanations for these facts are well beyond the demands of the UK and all this stuff. Some things you just have to know. Alright, I'm actually gonna this is for the Reddit post. I mean, sorry, not for the Reddit post. For the, I mean, it would be a pretty good Reddit post. Goes on Reddit post mid full. Not Reddit, dude. My fault. So again, higher temperatures increase elimination. You can just imagine this as like, you know, like when you increase higher temperature, you can become more angry, so you want to eliminate more. Some type shit. Water is like peace, so it encourages substitution. Ethanol like burns, so it encourages elimination. Okay. Then in concentration, high concentration for so you get like more stuff in there. So like more war, more angry, so elimination. And in summary, for a given halogen alkane, to favor elimination rather than substitution, use. So if you wanted elimination, you would use heat. You would use a concentration of a more concentrated solution, and you would use pure ethanol as a solvent. Oh, dude, that's why they said. Holy shit, that's why they said. Bro, they said ethanol, not ethanol plus water. Bruh, alright, bro. The thinker, we are the thinker. I'm sorry. Okay. And also, I mean, I don't know why they didn't mention that, but the halogen alkane itself should be tertiary. But okay, cool. Cool stuff, cool beans. Cool beans. I'm actually in a good mood, so you know, we're gonna hold on. Shit. Whoops. BRB. Alright, back real quick. We are chill as hell right now. I'm like, oh my god, I'm so happy right now. Hell yeah. Like, hell yeah. Okay, let's keep going. So, why? Oh shit. Okay. This is okay. This is kind of cool. Okay, so we're talking about like we're just comparing the roles of hydroxide ions. So, in okay, so this is a recap for us. So, a substitution reaction between halogen alkane and OH, the hydroxide ions are acting like nucleophiles. Okay, for example, the lone pairs can attack the slightly positive carbon. Again, lone pairs can attack the slightly positive carbon. Okay, I don't know why just remove this shit and put this H like somewhere else just to make it easier. Your C is going to be slightly positive, your Br is going to be slightly negative. So it attacks the slightly positive carbon. Okay? Now, if it attacks the slightly positive carbon, this leads to the loss of bromine as a bromide ion and the OH becomes attached. So it attacks the slightly carbon, and it forms that bond, and then what that happens, it leads to the loss of the bromide ion. This will go there, and it will exit as Br negative, dun dun, and yeah. Now notice they use the term, it attacks one of the lone pairs on the oxygen, okay? Because in this case, the oxygen would have a lone pair, would have a missing lone pair, or something like that. No, oxygen wouldn't. It would have a missing one. Then it would be like a dated bond. I believe. I think I heard this exact same statement today in class while I was like taking a nap. Oh man. Okay, the role of bro. How much more shit do we have to study? God damn. Brother, oh my god. Oh. And you're gonna have. Okay, I mean, it's one. I'm pretty sure that one is quite similar. Then you go straight to ammonia. If you're working towards a UK-based exam and don't have any idea, don't have any of this information, then it is essential that you get it. Okay, let's check. Do I need this? How do I check? 1 second, gang. 1 second. Okay, I'll actually pause the video because this is not a good idea to just let this run. Unfortunately, we do need it. We do need it. That is unfortunate. Where's my thing? Alright, there we go. Yeah, everything looks fine. So, we'll go through this. Here's the links. You can seriously lost. True. After making that, then you just talk about bromoethane. Then you have the silver nitrate solution. Do we have that? I think we do, yeah? No, we didn't. I think we do. We have cyanide, which was the first one. Then we have silver nitrate, yep. Then we have ammonia, yep. Then we have potassium hydroxide. Yeah, okay, so ethanolic potassium hydroxide by elimination reaction, that makes total sense. Not sodium, however. Okay, dude. Alright. This is crazy. There's just so much shit to learn. Comparing halogen oxide. Okay. This is going off of silver nitrate. Then we talk about Gringard reagents. Is this there in my spec? Because this is not familiar. It's called what again? Grignard. Grignard. Oh hell no, Grignard is all the way in top 20, bro. My fault, man, my fault. Okay, so this is not coming in this spec. And going below that, you're gonna get your uses. So CFCs, chlorofluoro. I thought we would never have two. Goddamn! I thought we would never have two halides on one thing. I guess we broke that rule. Okay, fine. So CFC, chlorofluoro. Wow, there's literally no CFCs. Are you serious? Well, I mean, I'm not too surprised the last two are not really discussed because come on, like this is probably like B level type shit. So we have nitrate solution and ammonia solution left to discuss, and also cyanide. Oh, I'm gonna shoot myself. Oh my god. Okay, what were we talking about here? Sorry, I got distracted like really bad. Leads to loss of bromine ion. Yep. Strong tendency, yep. Strong tendency to combine with hydrogen ions to make water because it's a base. Elimination reaction, hydroxide hits the hydrogen atoms, pulls it off. Leads to cascade effect, formation of carbon-carbon double bond. Yeah, yep. Competition between substitution and elimination is a rich source. You'll probably find that questions center around secondary hydrogen and carbon, like 2-bromopropane, because these can be easily persuaded to do either reaction. If the elimination mechanism is under syllabus, you are quite likely to be asked about questions in which the substitution reaction crops up as well. If you need to revise this in detail, now is not a good time to do it. True statement. Okay. Let's go. It's 12:41. I don't know if I want to do this. Okay, we're changing the bump one thing. I know we're editing this like mid one, but like we're crying now. Like this shit is tragic. Actually, like no, this is me. Like, this is distracting. Is this like distracting having this like go up every single time? I think it is kind of distracting. Okay, we'll switch it. Switch it to like the sad version. Yeah, I'm like really like depressed right now because this is just not it, man. This is just not it at all. Okay, let's go. I hope you're enjoying this. I don't know who the hell is going to be watching this stuff. Reactions between halogen alkanes and cyanide ions. So, halogen alkanes, cyanide ions, so haloalkanes, wow. I'm losing it. Okay, so first of all, we're already having sodium potassium cyanide solution, so we're still going off with the two classics. Separate page for the mechanisms. So you have your replacing halogen by Cn, okay? That's going to be your, so before it was OH minus, now it's going to be your Cn minus. Halogen alkane is heated under reflux with a solution of it in ethanol. Okay, this is almost the exact same. This is good news for me. The exact same. Also for you if you're a chem student. The halogen is replaced by a CN group and a nitrile is produced. So simply, instead of the OH group being replaced, now a nitrile is produced. Okay, so let's highlight the nitrile part. Heating under reflux means heating with a condenser. So if you like just learn this definition, it's important. Heating under reflux means heating with a condenser placed vertically across to prevent volatile substances from the mixture. This all is important. If a water is present, you tend to get substitution by OH instead of CN. Wait. Where's the OH coming from? I understand substitution from OH, but where's the OH coming from? From the water itself? Solution from potassium cyanide in water. Because in the previous case, the OH is brought in by the potassium and sodium, potassium and sodium hydroxides. Wait, is it? I don't even remember. In this one, it would be, yeah, sodium hydroxide, potassium hydroxide. So I'm not sure. In this case, OH is just coming up from somewhere. So a solution of potassium cyanide in water is quite alkaline and contains significant amounts of. Oh, fine. So when you have potassium cyanide in water, it will contain significant amounts of hydroxide ions that form an interaction between the cyanide ions and water. These react with the halogen alkane. I see. So, wait, hold on. Potassium cyanide. So you have potassium cyanide in water, right? In the solvent. If you use the solvent instead of water, if you use the solvent water instead of ethanol, then you have H minus ions, OH minus ions that would form, which would then react with halogen alkane in a nucleophilic substitution. Okay, makes sense. We can actually highlight that because that makes sense. Yeah, okay, let's go with that. And we'll just call it NS. Right, bromo, for example, using one bromopropane as a typical halogen alkane, so we'll form it like that. Br gets replaced with CN and BAM. Full ionic ones, KCN and KBr. Bromine or other halogen is in halogen alkane is simply replaced by CN, hence a substitution reaction. Notice how for all of these we have not seen a change in the thing in the halogen. It's literally been bromine every single time. So this is how you know it's every halogen acts the same way. Okay, hence the substitution reaction. In this example, butane nitrile is formed. When you name nitriles, you have to remember to include the carbon in the CN group when you count the longest chain. Example, there are 4. So remember, although this is its own group, you count the carbons. 1, 2, 3, 4. There's 4, so you're gonna have your butane nitrile. Okay. Secondary and tertiary halogen alkanes act similarly, although the mechanism would vary. I'm guessing the mechanism is going to be literally the NS. I'm praying so I don't have to study more. It's gonna be the NS1 NS2 thing. So let's see. Okay, I think this is it. So, simple facts uncovered, nucleophilic substitution between halogen alkanes and cyanide ions. Reaction between primary, so we're talking about straight up into primary halogen. So, halogen is, okay, so we're given definition. I'm going to highlight it every time so I don't try. Under reflux, in ethanol, halogen is replaced by CN group and nitrile is produced. Heating under reflux means heating where the condenser placed vertically in the flask to prevent loss of volatile substances from the mixture. Every single time we're going to highlight that shit. Solvent is important. If you present, yep. Oh, this is a much more simpler way of doing it. For example, one bromopropane is a typical, yep, okay. The mechanism. The mechanism looks like this. Okay, so we have the triple bond in the CN, and we're going in to the positive delta positive carbon, and you have delta negative Br. Okay, So this will fall. This will be a nucleophilic substitution because it involves two species. It'll be SN2, and you'll have this. So you're pushing out the BR and you're getting the CNN. And if your examiners want you to show the transition state, then it'll look like this. I doubt that they would. I can check. Transition state. Nope. So this is something I talked to my teacher about. So yeah. If I can even wake up tomorrow, it's 12:49. Type shit. No. Okay. My fault. Reaction of tertiary haloalkanes. So okay, again, it'll be NC2. I mean SN2, because two species negative. This whole thing is negative, and we're going to this pushes out the BR. And now if you have tertiary, this will be the exact same thing. We're gonna highlight this shit again. Heated under reflux with a solution of soda. Yep. Replaced by CN. Natural is produced. Okay. Has to be ethanol. Has to be reflux. Condenser. Volatile. Garbage. So then you have this again. You have your C, BR. Your three more. It's gonna be your CH3s, and your CN is gonna attack one of the it's gonna be attacking your C. And I'm pretty sure, without even reading, I can guess this. So BR is going to be, you have delta negative, this was going to be delta positive. So what's going to happen is first, this is going to break, so this is going to go over here, heterolytic fission. So that's going to be C plus with your little 3's and your BR with a double N minus. Okay, and then it's going to come in real quick in a fast step, and it's going to be your this and 111C, or is it the other way around? I don't think it really matters. And you have your negative, and then it's gonna lead to C and C Okay, let's see. So your slow step will be this breaking off, and you have your positive and your negative BR, and it comes in. The C is the one with the negative, and it's fast. So then you form this. Okay, you make sure you want to write down the triple bond. Oh, sorry, it's a single bond between the C, and then a triple bond between the N. Okay, let's get a triple bond between the N. Very ugly. Sorry. C, another C, and then a triple bond with an M. Now this is an example of nucleophilic SN1. Now if you have secondary, then you can have both. We're not forgetting this shit. Haloalkanes heated with a reflux solution, blah blah blah, and ethanol. Okay. SN1, SN2. SN1 would look like this. Okay, yeah, I do want to see what this looks like. So it's in the middle. This attacks the top. Attacking the top. This is gonna go out. So you're gonna have this, and you have this formed up on the top. And then in this one, the BR would break first, giving the thing, and you would come in. These are already two, so you would come in and bang, because it's already forming a bond with the H. Okay, now, oh my god, we have to explain these? Is the explanation gonna be different? Bruh, the explanation's gonna be different? Okay, well, I am being kind of lazy because there is like the C triple bond stuff, which I'm not really paying attention to. Okay, I mean, if it's easy, then I can get through it really quickly, so I'm not too worried about it. I understand that I have two more topics. I have ammonia, another thing, but I want to go through everything, dude. Am I really gonna study the entire thing? I don't know. I have to go to sleep soon, man. That would be insane if I actually studied the entire thing. Like, that would actually be insane. I was joking about it, but I don't know if I'm actually gonna do it. Okay. reactions between primary and secondary halogen alkanes and cyanide ions, SN2 mechanism. Cyanide is nucleophiles. Dude, imagine I do all this and just because of the music that I'm playing in the background, like the entire thing gets cancelled. Like a literal copyright strike. That should happen, man. That should be tragic, bro. I'm literally. What am I doing? Okay, I'm sorry, guys. Cyanide ions as nucleophiles. Okay, yeah, we know that. It's something that's strongly attracted. Okay, so just defining it. This is actually important because I didn't really know this. So it's a species strongly attracted to a region of positive charge, which is usually the carbon delta positive and something else. Nucleophiles are usually fully or strongly negatively charged, and in the case of cyanide ion, there's a full negative charge on the carbon as well as a lone pair of electrons. Okay. There is a lone pair on the nitrogen as well, but to avoid confusion, that one on the carbon is more important in this instance because that's where the negative charge is. The combination of the lone pair and the negative charge makes the carbon end of the ion the nucleophile. Okay, so this seems pretty important as well. Okay, there are two. However, the one on this side is more relevant because the combination of the lone pair and the negative charge makes that side the nucleophile. Look, there is the one on the carbon is more instance because that's where the negative charge is. So there's two things here. There's two lone pairs, but there's only one negative charge. Negative charge is over here and lone pairs over here. So just to avoid confusion, we don't write the lone pairs here, we write the lone pairs here. Because you kind of tend to associate lone pairs with negative charges, even though they're not really the same thing, because that's what I just learned. Even though I thought that was the same thing, but I guess not. Okay, nucleophilic substitution, SN2 reaction. We'll talk this too with the primary halogen alkane. If it's primary, then you're gonna have this. Is this like... Oh shit, okay, this looks kind of like tough, alright. I think we went to the explanation for nucleophilic, huh? There was explain. I don't know, anyways. So, we're talking about a primary halogen alkane to start with, and yeah, the bromoethane has a polar bond between the carbon and the bromine, of course. So simply to draw it, you're gonna have the cyanide. You're positive, you're negative. Okay. In an exam, you must show the lone pair, of course. Doesn't matter. Lone pair on the carbon end of the carbon of the cyanide will be strongly. Yep. Move towards it, beginning to form bond with it. The approaching negative ion will repel the electrons in the carbon bromine bond closer. Okay, here we go. So the approaching negative ion from the CN will repel the electrons in the carbon bromine closer and closer to the bromine until at one point they'll just enter the bromine, right? So at some point the CN and the bromine will be both half attached to the carbon. This is called the transition state. Ah, okay. So the NC is getting closer to the C, and so the electrons from NC is getting closer to the C, and the electrons from CBr is getting closer to the BR. And at what point they are both half bonded. One is about to enter, the other one is about to leave. It's kind of like the limiting equilibrium in mechanics. That kind of reminds me of that. It's about to start moving because the applied force is equal to the friction. Like it's literally about to start moving. Okay, so This is called the transition state. It's not an intermediate. You can't isolate it, and it doesn't have any independent existence. It's just a halfway station through a smooth movement of atoms and electrons. The movement goes on until Cn is firmly attached and the Br has been expelled as Br ion. You may need to show that the formation of intermediate is in the mechanism. It simply needs you to draw the mechanism showing some more detail. Be very careful when you draw the transition to make a clear difference between the dotted lines showing a half made and half broken bond and those showing those bonds going back into the paper. Oh, you need to do that? Wait, oh shit. I didn't even notice this entire time. They've been drawing the things in 3D. Oh wow. Okay. Notice that the molecule has been inverted during the reaction like an umbrella going inside out. Sure, I suppose. You're going like, and like you're having these things pointing inwards. It would be like, you're this, and then you're kind of going like this. And then it goes into like kind of just like, yep. If you aren't happy with the various ways of drawing bonds, it's important to follow this link to find out exactly what these symbols mean. Important to know the ways of drawing these. If you haven't checked, then do so at the time of writing at Excel. For example, wanted the transition state included. Oh shit. Like, wait, hold on. I'm doing at Excel. At the same time of writing at Excel, for example, wanted the transition state included, and that isn't obvious from their syllabus. You have to check mark schemes and examiner reports. Bro, we have to do the transition state. Why? Technically, this is known as SN2 reaction, is it? Yeah, of course it is. Nucleophilic substitution. Yep. SN2 in secondary halogen alkanes. So it's the same exact thing. Reactions between secondary and tertiary. The SN1 mechanism. Are you sure? How do I have syllables? Several syllabus restricts you to primary halogen alkanes. I doubt that. My one does. Okay. Start with, we'll talk about this mechanism through the tertiary halogen alkane like the one on top right. We got 2-bromo. So this is a tertiary one. Okay. Now, why do tertiary halogen alkanes need a different mechanism? Oh, they do? Wait, okay, this is kind of sick. When a nucleophile attacks a primary halogen alkane, it approaches from the side away from the halogen atom. Yep. Any other approach is prevented by the halogen atom is both bulky and slightly negative charge. The charge repels the incoming nucleophile. With the tertiary halogen alkane, this approach on the back is impossible. The back of the molecule is completely cut out. We actually studied this today in my class. The SN1 mechanism, the reaction happens in 2 stages. In the first, a small proportion of halogen alkane ionizes to give carbocation and a bromide ion. Yep. The reaction is possible. So again, it's just the theory behind why this happens, which is exactly this, because the nucleophile wants to attack carbon from the side away, but but it's prevented by the halogen atom, which is both bulky. But the problem with tertiary, and it's only with tertiary. Oh, so that's why tertiary only has, or rather, yes, tertiary only has SN1. Bruh, okay, I understand it now of all times. I feel like this would have been a thing I should have been able to understand before. But anyways, it's impossible because the back of the molecule is completely covered. So just cannot. So the front side there's a halogen, and the back side there's 3CH3s. Yes, this thing right here is actually the carbocation. So the reaction happens in two stages. In the first case, a small proportion of halogen alkane ionizes to give a carbocation a bromide ion. This reaction is relatively possible. This reaction is possible because the tertiary carbocations are relatively stable compared with secondary or primary. So as you remember, the tertiary ones, which are to 3, are the most stable. So since they are the most stable, they are the most common, so this is possible. If it was primary, then it would be less possible. But even so, the reaction is slow. Once the carbocation is formed, however, it would react immediately in a fast reaction with the CN ion. The lone pair is strongly attracted to the positive carbon. How fast this reaction is governed by how fast the halogen alkane ionizes, because that's a slow process. Interesting. Because the initial step only involves one species. This initial step is slow because it involves one species only. The mechanism decides SN1 nucleophilic and is taken in the initial slow step. The SN1 mechanic is in secondary halogen alkanes. It can go SN1 or SN2 to the back of the molecule. It's rather more cluttered than in the primary, but there's still room for the lone pair on the nucleophile to approach and form a bond. We've already dealt with that reaction. It is possible to get some slight ionization to give an SN1 reaction, but this reaction is much less successful. Because, this is important, the reason why SN1 mechanisms is less successful is because the secondary carbocation ion is formed and it's not as stable as the tertiary one. And once the carbocation ion is formed, it will react immediately with a cyanide ion, as usual, forming a bond. Okay, well, yeah, I definitely learned that, made the connection between carbocations and the thing that we learned today. So I'm glad I actually read through this. So yeah, that's done. Where's my dog? Wait, what? Oh my god, no way, I just deleted it. Oh, that would be so bad. Okay, BRB, because this is a pain. Okay, not sure what happened, but we got it back. We got it back, baby. I'm feeling kind of good right now, so let's just like, we chilling out here. Alright, so, okay, now why do these reactions matter, right? So, I do remember, before we continue, I do remember talking about, I do remember hearing about cyanide being used to form something else. So, here we go. Cyanide ions is a useful way of lengthening carbon chains. There you go. For example, in the equations above, you start with 3 and end up with 4. There aren't very many simple ways of making new carbon-carbon bonds. It is fairly easy to change the CN group at the end into other groups. If you want to find more about nitriles and the reaction with the CN group, you could explore this. So what they're seeing is, by the end of the thing, right, if you had a Br, and then you replace that with a CN, then now you have a new CN. Now there's a way to remove that N, to remove the CN group and form it into a new group, for example, like a CH3 group, right? Or like like the N gets removed and then you put on like a CH, like a triple one C, right? Or maybe perhaps you remove that N and form another CN and then another CN. But then these would also need hydrogen, so I'm not sure how that's gonna happen. So now we're talking about ammonia? Yeah. So this takes a look at halogen alkanes and alkyl ammonia is especially a very complicated series of reactions. Important you know exactly what your examiners want. I don't really care. Current summarize the main facts. If you need details, you'll find in the link below. So reactions. So halogen alkane is heated. It's okay. It's already different. God damn it. So it's heated with concentrated solution of ammonia. Okay. So ammonia and ethanol. Ethanol is going to be your solvent. Ammonia is going to be your reactant, and it's going to be concentrated solution. Before we had like concentrated solution of like potassium or sodium, you know, hydroxide or cyanide. This time we just have straight up ammonia. The reaction is carried out in a CO2, and you couldn't do this under reflux because ammonia would simply escape as condenser as gas. Okay, so this is carried out just in a CO2, and not because ammonia would simply escape as a gas. Now we'll be talking about the reaction using 1-bromethane as a typical primary halogen alkane. There's no difference in the details. If you choose a secondary or tertiary, the equations would just look more complicated. You'll get a series of amines formed, and amines, if I'm not wrong, is your NH2s, okay? Or perhaps it's NH3, I don't know. The reactions happen one after another. So you get a series of amines. You got like one after another, kind of like your chain reactions when we were doing the stuff with the electrophilic addition or something. I don't remember. So when you break up primary amine, the reaction happens in 2 stages. In the first stage, salt is formed. In this case, ethyl ammonium bromide. This is just like ammonium bromide, except that one of the hydrogens in the ammonium ion is replaced with ethyl group. So one of the hydrogens in the ammonium is replaced by ethyl group. What the hell is happening? Actually, I have no idea what's going on. In the first stage, a salt is formed. Now, this is just like ammonium bromide, which is literally NH3Br, except that one of the hydrogens in ammonium ion is replaced by a thing. Now, see, what we're looking at okay, I'll need to look at the mechanism for this because I'm already kind of confused. There is then the possibility of a reversible reaction between this and excess ammonia in the mixture. Oh god. So more NH3s reacting to form CH3CH2 and NH2 plus NH4Br. The ammonia removes the hydrogen ion from ethyl ammonium ion to leave a primary amine, ethylamine. The ammonia there is in the mixture. The more ammonia, the more forward the reaction. Find a considerable agreement in textbooks and sources about the exact nature of products. Some information you'll come across is simply wrong. You can read the arguments. Warning that page is in the mechanism section of the site. Wait, so like, are we going to be talking about the mechanism now, or? This whole reaction is complete pain if you are going to learn it. It is much easier to work it out if you need to, provided you understand mechanisms. That's what I'm saying, and I want to look at the mechanisms. Okay, I mean, I kind of understand this. So basically, you have your like Where's that done? Okay. You have your NH3 and you have your Br, right? And it kind of forms a bond between the Br and the and the CH2, right? So imagine you have your C, Br, and now this NH3 is coming in, and what it does is basically just comes in between. And I don't know how it would do that, but apparently it does. And you go in them like this. Like you have delta positive, delta negative, or no, it's literally saying positive, negative. There's a possibility that, okay, after this is formed, then comes in another NH3 group. And then in that case, what's going to happen is, I'm guessing one of the hydrogens from here is going to go. And it's going to be only an ion. So the bond, let's say this was like, right? So then that hydrogen will go into this. This will be used to get rid of this, which then causes more electron pressure into Br. So then it'll take the electrons with it and it'll go into this, causing it to go NH4 plus and Br minus. If I'm right about that, that would be insane, but I doubt that. Oh no, I'm yawning like crazy, dude. I'm yawning like crazy, man. Alright, so the reaction doesn't stop at a primary amine. Diethylamine also reacts with bromoethane. Wait, are you serious? Wait, why are we talking about primary amine? So now we have so I was right, but the NH2 being counted as an amine group, and it's counted as primary amine because the NH2 is bound to an alkyl group which is bonded to only one CH3, as we're seeing here. So then that ethylamine this is now called ethylamine, by the way. This is called ethylamine. It's easy to understand. This is amine, this is ethyl. 2 carbons. So now the ethylamine will react with another bromoethane, which is going to be your starting, primary halogen alkane in the same 2 stages as before. In the first stage, you get a salt formed, this time diethyl ammonium bromide. Think of this as the ammonium bromide with 2 hydrogens replaced by ethyl groups. What on planet Earth? What on planet Earth is that? So you're telling me you have your C and your Br, right? Your 2 H's. Then this crazy guy comes in between, forms the NH2 bond, makes this negative, this is positive, this connects with the rest, and it has already been connected with its own CH3 CH2. So now this is actually the same, this is actually the same, so it's going to be called diethyl ammonium bromide. So you're having 2 ethyls, right? So you're going to have diethyl, and then you're going to have ammonium bromide. Now, there's again the possibility of a reversible reaction between the salt and excess ammonium. So then, if you have this reacting with NH3, Right, so now NH3 comes into this. If NH3 comes into this, then you're going to get, again, one of the hydrogens from here going into here, breaking that, and one of the things going like this, and then that's going out back over there. So that's going to form NH4 plus Br minus, which is, you know, the same exact product that we saw in the primary one. Leaving the amine has something like, so we're going to have two of those ethyls bonded to an NH. Then the ammonia with a hydrogen, yep, to leave a secondary amine, diethylamine. The secondary amine is one which has two alkyl. So now it becomes a secondary amine. Oh my god, it doesn't stop there. And so an NH is also considered an amine. Okay. And it still doesn't stop. The diethylamine also reacts with bromoethane. Holy shit, dude. Enough. Okay, so let's predict what's gonna happen here. So you have your CH2, or rather it was C with the Br going up down, and we have your NH going with the two little guys, and then would be your C with your NH going with the two guys, and this is actually just going with that guy, and then it goes with the Br, and N is going to be positive, B is going to be negative, plus is going to be positive. So it's going to be diethylamine, or triethylammonium bromide. Ammonium will be when you have the ion, and amine is going to be when you have the solid thing, okay? So then the reversible reaction, where you have NH3 going to come in, right? And so this goes over there, this goes over there, because this removes, so this goes over here, and this. So then as a result we have the bonded to N, bonded to B, bonded to B, bonded to nothing else, plus NH4 plus Br minus. Then the ammonia leaves the hydrogen ion from the triethylammonium ion to leave a tertiary amine, triethylamine. A tertiary amine is one which has three alkyl groups attached to hydrogen. Okay, are you kidding me? We're doing another one? Oh, because the nitrogen can only be 1 to 4. Oh my god. Oh my god. Triethylamine reacts with bromide to get tetraethylammonium bromide, quaternary ammonium salt, one in which all 4 hydrogens have been replaced by alkyl groups. And now, since there's no hydrogen left on the nitrogen, the reaction just stops there, and it is left as a ammonium salt. Remember, it's left as ammonium, not amine. So you cannot have a quaternary amine. You can only have tertiary amine. Bruh. That is insane. I mean, that was just so crazy. That didn't even seem real. But yeah. Okay, the mechanism is not going to be that hard, because for the most part it's literally the same thing happening over and over again. Where's our little guy? Did I download it? did. No, we didn't. Halogen alkanes and ammonia. We did. Crap. I should be paying attention more. Sorry, guys. Damn. I'm washed. The boy is washed. I want to take a break, but I don't. This page gives you the facts in simple and clear. Yep. Produce primary means, because it's the exact same thing for any other one. Make sure you know it's concentrated ammonia in ethanol, CO2, because ammonia is gas. Reaction happens in 2 stages. The salt formed. So there's 2 stages. One is where the ammonium salt is formed, and the next is going to be when the amine is formed and the NH4Br minus is formed. Okay, so this happens in 2 stages. At first stage, the salt is formed. In this case, it's this ethyl ammonium, but then it'll be di, then tri, then tetra. This is just like ammonium bromide, except that the fact this is just like ammonium bromide. I don't know what ammonium bromide is. Except for the fact that one of the hydrogens in this ammonium ion is replaced. Okay, we have already explained those. And the mechanism. First is a simple nucleophilic substitution. You have N with the with the 2 electrons coming in, and you have Br. So it goes into the carbon, forms a bond. This is gonna break off. And now you have this. Because the mechanism involves collision of 2, it's SN2. In the second step, but see, there's a problem. That's not. Wait, am I literally reading this wrong? Have I been reading this wrong this entire time? That would be really unfortunate. Oh, that's why it's hidden. Okay, we have too many tabs open basically. Let's close some of these. Alright, let's just move nucleophilic substitution of ammonia. Okay, so if you look at this, and you look at the bromines, while we're doing this, are these bromines connected or not connected? Is this bromine still involved within these 2? Because the mechanism does not say that. So it literally says the bromine is leaves. The second step of the reaction, an ammonia molecule may remove one of the hydrogens on NH3, and ammonia is formed together with the primary amine, in this case ethylamine. What did they say? Yeah, an ammonia ion is formed, NH3, because, okay, so an NH, so double bond over there, sorry, electrons given over there, so this goes over here. Brings your H over. Okay, yeah, so the things are just left over here, and this goes as a plus. Your product will therefore contain ethyl ammonium ions, ammonia, ethylamine, and ammonium ions. Wait, but this is not what we're talking about here. What? Okay, so I'm starting to think that the Br and NH4 don't actually combine together. But they literally do. They say triethylammonium bromide. Bromine is involved. I'm so confused. Oh my god, bro. There's more. Oh my god. Oh my god. Alright, we're quitting it, dude. We've been at this for 3 hours. I can't do this shit anymore. I can't. I can't do this shit. I'm sorry, guys. I wanted to, but hey, I mean, look how far we got, bro. Like, we got hella far, bro. I mean, especially the fact since like we just need silver nitrate as the last one. That's the last one, and then we're done. And like, of course, silver nitrate is not easy. It's not easy, but I mean, ammonium is probably the hardest one to get. Like, literally, there's so much shit. There's just so much stuff. I've never looked at this many equations in my life. Okay, let's just shut up, man. Just shut up. I need to know this. I need to know why this is. Ammonia's nucleophile species, okay, blah blah blah. Ammonia doesn't carry negative charge. However, nitrogen is more electronegative than hydrogen. So nitrogen carries some degree of negative charge. It also has an active lone pair. Attack on plus. Carbon on the halogen is the lone pair. Toxins with bromethane. Lone pair on nitrogen was strongly attached to that. So ammonia is firmly attached and expressed as Br ion. Notice that the nitrogen in this product ion carries a positive charge, highlighted in red to draw attention. That charge has to be left there for two reasons. On the left hand of the equation, you start off with two neutral molecules. Assuming you forgot about the positive charge, you would end up with a neutral species and a negative ion on the right. Charges must balance an equation, so something is wrong. The nitrogen looks wrong. The nitrogen atom is joined to 4 things rather than its usual 3. Nitrogen can only join to 4 things if it carries a positive charge. Technically, this is known as SN2. Prior to this, it's called ethylene bromide is a... Okay, so... Still have no fucking clue. I still have no clue what is going on. Can you still hear me? I don't even know if my mic can like pick up on this shit. Cause I'm literally like muttering at this point. Okay, ethyl ammonium bromide is a salt of primary amine and the acid HBr. A primary amine has that. Okay. So we're getting the salt name. Okay, so the first one of all the 4. This salt is a salt of a primary amine, okay, and the acid HBr. What? What acid are we talking about? Is one of the hydrogens bonded with Br to form HBr, a hydrogen halide? Dude, I have like literally no clue. Like, what on earth is happening here? A primary amine has the formula RNH2. It is primary in the sense that there's only one alkyl group. Primary amines are weak bases very similar to ammonia. Primary amines, weak bases, so they form salts with acids. For example, ammonia reacts with HBr to give ammonium bromide NH4Br minus. Oh my god. That's how they explain it? Oh my god, finally. Your excess ammonia will react with HBr to give NH4 plus Br minus. The salt in the equation above is the one formed from this. So what they're saying is this actually turns into an HBr. We can't see that, but it somehow turns into an HBr. Now when it turns into an HBr, then when that second thing comes, then they're going to take a hydrogen from the NH2. They're also going to take the Br with it, and so if it forms a bond with the H, then it'll be positive or negative. I'm not sure. It says HBr. Primary in the sense that there's only one alkyl group attached to nitrogen atom. Primary amines are weak bases compared to ammonia, and so they form salts with acids. HBr is an acid. So then ammonia, in this case, ammonia is going to be your NH4 plus, okay? It's going to be this thing. This is going to be your ammonia, okay? Even though it's NH3 plus the CH2. Now, since the NH3 is a base and HBr is a salt, it'll give ammonia bromide NH4Br, and the salt that we're talking about, the salt in question, is going to be this salt. Right here. However, over here there's no H. There's no H. There's no H. I don't get it. I just don't understand. There's no HBr. There's no HBr. I don't get it. I don't get the salt. I don't get the salt. The only way I can understand this is the positive plus on an H binds with the negative Br, forming an HBr acid. Then you have that NH3 coming in, NH3 plus your HBr, that's an acid, that's a base, you're going to get your NH3 4 plus, NH4 plus Br minus. And then the salt, the equation above, is formed from ethylamine, forming HBr, CH3, CH2, NH2. Yeah, that makes sense. That makes sense. Take 1 second step. The ammonia molecule now removes a hydrogen atom from the. So we see an NH3. We see the hydrogen. We see then okay, N plus. Okay. The organic product is ethylamine. right? Because you're left with the N lone pair and NH4 plus. Now notice that this change is reversible. The curly arrows can reverse the change. How been shown to avoid confusion. You can easily picture the lone pair on nitrogen reclaiming its hydrogen from the NH4 plus. What will you end up with the mixture of all four? Together, you're going to have bromide ions. Okay, bromide ions is going to be your Br minus. Sorry, you're going to have bromide ions from the first stage. I haven't written jack shit in a while, but yes, you're going to have bromide ions from the first stage. You're going to have proportion of ammonia in the original reaction mixture, right? Because you're having concentrated ammonia in ethanol. And the greater chance of the higher the proportion of ammonia, the greater chance of the free ethylamine being formed. Free ethylamine being the ethylamine with the lone pair. And the reaction between tertiary haloalkanes and ammonia, that's one. Now, why do tertiary mechanism use a different mechanism? Because it blocks, right? Okay, yeah. So it breaks off the Br first, NH comes in, makes the thing. How fast? Yep, it's the same exact thing. N double bond puts the lone group and goes off with NH4. Further substitution of these reactions, let's check it out. Yeah. Only one. Don't even think about reading this page unless you're confident about nucleophilic substitution. Regarding this, you need to only worry about that. These reactions on the current, they are no harder, but they do look more difficult. They are certainly much more tedious. It's more important. It is important that you understand what is explained on this page. Life is too valuable to waste it on learning each of these reactions described here. If you understand what's happening, you can work out the equations if you need to. Oh my god, what is going on with this page, bro? I'm opening this shit, just 1 second. What is happening on this page that like my life is like in his hands? Like bro, look at this forewarning, holy shit. So we're talking about why are we getting multiple substitutions? So the lone pair on the nitrogen is in an ammonia group is attracted to the salt is formed, primary amine has the general formula RNH2, this reaction is reversible and you only get significant amounts of free amine if you lose a large product is a nucleophile. So at the end initial substitution, there will be a certain amount of free primary amine formed. Because I have a double bond in the example above. There may not be much of it, but there will be some. If that small amount reacts with something else, the reverse reaction can't happen any longer. The free amine will continue to be produced, and what was originally a reversible reaction becomes a one-way reaction provided the free amine is removed by the other as soon as it's formed. What the flip are you saying to me? At the end of the initial reaction, there will be a certain amount of free amine. In the example above, there may not be a lot of it, but there will be some. And if that small amount reacts with something else, the reverse reaction cannot. Okay, no, that makes sense. Yes. I was thinking if the reverse reaction reacts with something else, as in like reacts with what it's supposed to react with, but no. If it reacts with something else, then it can't happen any longer. The free amine will continue to be produced, and what was originally a reversible reaction becomes a one reaction provided the free amine is removed by some other reaction as soon as it's formed. Compare the structures of ammonia ethylamine. NH3, 2, what's that? You can think of the primary amine as a slightly modified ammonia molecule. It has a lone pair of nitrogen bigger structure than an ammonia. That means that the primary amine is going to be a better nucleophile than ammonia is. And you can therefore get a reaction between it and a molecular halogen alkane. Holy shit. I'm making a secondary amine from a primary amine. So you have that, and you're gonna break that, and you get formed that. The lone pair on the nitrogen in the primary amine attacks the lone pair on the nitrogen in the primary amine attacks the carbon. Bromine is lost, and the immediate product is called diethylammonium bromide. Yep. And this is essentially ammonium bromide in which two of the hydrogens are attached, have been replaced by ethyl groups. Yep, we've seen this before. They're organic, so we see this as it bonds with your H group and forms NH4, leaving the two lone pair. The organic compound is a secondary amine, diethylamine. It is a secondary because there's two. Tertiary. Wait. Oh no. What am I reading that's different? This is exactly the same thing. Oh, no. This is literally exactly the same thing. If you get a bromomethane and wait. Was that just because it was here? Ugh, are you kidding me, man? I mean, the only difference was this just contained that, but it doesn't really help me. Like the last topic. We're actually on last topic. 3 hours, 23 minutes on. Man, honestly, okay, we're gonna take some time off. I just want to talk about how insane this is for me. Because, look, okay, I am not a very hardworking person, and I don't really get into studies that often. And the fact that, I've been studying for 3 hours straight, okay, it genuinely means something to me. Because it means that this study method of me sitting in front of a camera and, just talking, it helps. There's something about it that I enjoy enough for me to sit in front of it for 3.5 hours talking about chemistry. I don't know, there's something about it which I just enjoy. I've never been this passionate about anything in my life, regarding studies. I've never been this straightforward and hardworking. Never. And I think that's a really cool change that I'm seeing happening. Is it a very healthy one? Because it's currently 1:48 a.m. So no, it's not necessarily a healthy one. However, it's still very cool to me. But anyways, I'm freaking out. I don't know what the hell I'm doing. Wait, actually, this goes hard. Hold on. Wait, what's over there that I shouldn't be blocking? Nothing. Alright. Let's go. Let's end this. Let's end this. Let's end this. Let's get this shit. Let's get this shit. Okay, so we have halogen alkanes in silver nitrate solution. So this can be used as a test for halogen alkanes, and this can be used as a means of measuring their relative reactivity. So these are the two uses of this that we know. First of all, you're testing for halogen alkanes. Silver nitrate solution can be used to find out which halogen is present in a halogen alkane. As you remember, cats with brains can cats with brains can ideally yodel. So you have your cats with CW, so your chlorine is white, B is bromine is creamy, and I is iodine is yellow. Sorry about that. So the most effective way to do is to do a substitution reaction which forms the halogen into a halide ion, and then do the test with the ion with a silver nitrate solution. So you do the reaction. Halogen alkane is warmed with some sodium hydroxide. This is your basic. Turn it into alcohol, like the most basic shit. Turn it into an alcohol. Make it ethanol and water. You know, drink it up if you have to. Yeah, you've done a lot of good work this time. So everything will be good. Everything will dissolve in this mixture and you can get a good reaction. So halogen atom is displaced as a halide ion. So you get the alcohol and you get the halide ion. There's no need to make this reaction go to completion. Silver nitrate is sensitive enough to detect fairly small. So the mixture is then acidified by adding dilute nitric acid. So that's the first step in reality. And this prevents unreacted hydroxide ions from reacting with silver ions to give a confusing precipitate. Then silver nitrate is added. Various precipitates may be formed, but this is how it is. One second. There's one point I didn't understand. Yeah, this. Am I aware of this equation? It's like you have your hydroxide, and it's the nucleophile, so it substitutes because you have your C, you have your H, or you have your X rather. Your OH comes in, goes over there, and this as this comes in, this will go out as your hal minus. That's it, right? Okay. And so it's like an ion, then you'll be able to detect it. Now, if you want to confirm it, it's actually quite difficult to distinguish between these colors, especially if there's not much precipitate. You can work it out by adding ammonia solution. So when you add an ammonia solution, then the precipitate dissolves to get a color solution if it's AgCl. If it's AgBr, then the precipitate almost unchanged using dilute ammonia, but dissolves in a concentrated. So again, this is like you put in some and then you put in more and then it will dissolve. And then AgI is just insoluble. Comparing halogen acts. Oh my god, we're so close. Holy shit. Oh my god, it's happening, don't panic. Oh, there's mechanisms. Oh, hell no. Okay. So, halogen alkane reactivities, background. In this case, various halogens are treated with, nothing else is added. After various time, precipitates appear as halide ions, with silver ions present. After varying length of time, precipitates appear as halide ions react with silver ions. As long as you're doing everything under controlled conditions, the time taken gives a good guide to the reactivity of the halogen alkane. And the quicker the time the precipitate appears, the more reactive the halogen alkane. Now, the halide is formed in one of two ways, depending on the type of halogen alkane you have present. Primary, secondary. Halide ion is formed in one of two ways. Am I tripping, or do I know this? is this talking about just the the two species, one species type thing? For primary, the main reaction is one between halogen alkane and water. Tertiary ionizes to a very small extent of its own accord. Sorry, one sec. What's going on here? First of all, I want to highlight this. And gives the time taken gives a good guide to the reactivity. The quicker the precipitate appears, as in the precipitate once you add in the silver nitrate, the more faster. Now, the halide ion is formed in one of two ways depending on the type of halogen alkane. That means when we mix that halide ion, when we mix the halogen alkane with the potassium or hydroxide. Wait, they said sodium hydroxide in this situation, right? Yeah. So when you have primary, the main reaction is one between halogen alkane and the water in the solvent. Which forms the H plus negative. Tertiary halogen alkane ionizes to a very small extent of its own accord. What? What the hell? Okay, okay, we do need to see the thing. Compare the reaction rates as you change the halogen. So now we're actually we have to keep the same type but vary the halogen. So this time, finally, halogen was going to be your independent variable, and the time taken through the judging by the reaction rate is going to be your dependent variable, and you would have to keep the type of halogen alkane constant but vary the halogen. You might, for example, compare these times to produce a precipitate. So again, you're going to want the same thing, you want the same type, but you would compare the times to create a precipitate from the series of primary halogen alkanes. Okay, same length obviously. Obviously, time taken for a precipitate halide to appear will depend on how much of everything you use and the temperature, but the pattern is always the same. A primary iodo compound produces a precipitate quite quickly. Primary bromo takes longer. Chloro probably won't give any precipitate until after you've lost the interest in the whole thing. That's hilarious. That is a fizzy certified lol. That is really funny. The order of reactivity reflects the strength of the carbon halogen bonds, and the carbon iodine is the weakest, and carbon chlorine is the strongest. And again, carbon fluoro is literally so weak that it wouldn't happen. Now, in order for the halide ion to be produced, the carbon halide halogen bond has to be broken. The weaker the bond, the easier that is. If you have looked at the mechanisms for these reactions, then you would have known that the lone pair on the water attacks the slightly positive carbon attached to the halogen. It is slightly positive because most of the halogens are most electronegative. Yep. Temperature think that the reaction will be faster if the electronegative difference is greater. The slight positive charge on the carbon will be larger if attached to the chlorine atom than an iodine atom. See, yes, you would think the reaction is faster. However, the slight positive charge on carbon will be larger if it is attached to a chlorine than an iodine, which means that there will be larger attraction between the lone pair on the water and carbon. The electronegative difference between the carbon and iodine is negligible. Wait, sorry. This means that there will be more attraction between a lone pair on the water and a carbon atom. Attached to a chlorine than if it was attached to iodine. The electronegative difference between carbon and iodine is negligible. right because they are so weak. However, the fastest reaction is going to be with iodoalkane. In these reactions, bond strength is the main factor deciding the relative rates. Comparing reaction rates of primary, secondary, tertiary, you would need to keep halogen constant, of course. It's commonly used bromides. If you used, so now compare these. Again, the actual times will vary with the reaction conditions, but the pattern will always be the same. Tertiary produces almost instantly. The time considerably longer. It is more difficult to explain the reason for this because it needs fairly intimate knowledge of the mechanisms, and it reflects the change the way the halide ion is produced as you go from primary. Okay, I was interested in this actually. I was interested in this. I don't know if I've read this before though. I hope not. Okay, I haven't. Because I'm actually really interested in this. And this is the last thing. This is literally like is this the last thing? Holy shit, guys, it's the last thing. Oh my god, it's the last thing. Okay. Oh, I wish I could show you how many files I have right now. There are literally some, like, there was that, the nucleophilic substitution between halogen and alkanes and ammonia. I literally didn't write a single thing on it. I'm like losing it, dude. Alright, last thing, boys, let's get this. So we were a bit confused about when water was reacting with primary and tertiary and secondary and all that. So let's look. As we know, it will be a slow reaction between primary halogen alkane and water even if they're heated. Halogen is replaced by OH. Yep. To form alcohol, ethane, and ethanol, whatever. It's produced by with hydrobromic acid. Be careful not to call this hydrogen bromide. Hydrogen bromide is a gas. When it's dissolved in water, there will be hydrobromic acid. So this is okay, fine. So this is important. So when you have a slow reaction, halogen is replaced. Okay, now using 1-bromethane as your typical primary, alcohol is produced. Okay, so alcohol is produced together with a hydrogen bromic acid. Not to call it hydrogen bromide gas when it is dissolved. It is called, when dissolved, called hydrogen bromic acid. And the mechanism itself states that when you have O with two thingies and this minus, and these are going to be plus and this is going to be plus, and you have this and this is plus and this is minus, then you're going to have one with a double bond, and you're going to have a positive charge over here, and this is going to exit over there. Because the mechanism involves a collision between two species, it's SN2. Now the nucleophilic substitution is very slow because water isn't a very good nucleophile. It lacks full negative charge of, say, a hydroxide ion. Now, the second step of the reaction simply tidies up the product. Water molecule then removes one of the hydrogen ions, hydrogen attached to it. Oh, I see. Okay, so again, the second step simply tidies up. Another water molecule comes and removes one of the hydrogens attached. Okay? To give hydrogens attached, to give an alcohol and a hydroxonium ion. So again, since we're removing, since this plus is there because it's lost one of the things, it'll go donate its electron over there. This will donate its electrons to the H. This puts its electrons back inside. This comes out with the H, forming a plus ion, hydroxonium, and hydroxonium and a full alcohol. Now, hydroxonium ion and the bromide ion from the nucleophilic substitution stage of the reaction make up the hydrobromic acid. So then this will form with the Br minus to find the hydrobromic acid, which is like HBr. Or something. hydroxonium ion and the bromide ion make up the hydrobromic acid. So this is literally it. HBr, although said by that, oh my god, this is, excuse me. So although it says hydrobromic acid up here, let's go up here. Where are we? Here. So we would have somewhere I got stuck. Here, right here, yeah, this very point. So you're gonna have, you have primary, you're gonna have ROH, H plus, and HAl minus. So your H plus, I believe, is going to be your, no, oh, what the hell's going on? Where am I? Hydroxodium ion and the bromide ion. Cha. How are we doing this? Hydroxodium ion. Am I an idiot? Or is it just 2 a.m. and I'm really tired? Okay. This is very confusing for me because, see, the thing is, we have the hydroxonium ion over here, and it's telling you that it bonds with the Br minus to form the hydrobromic acid. Cool. It's fine by me. However, when we just go up, then we're seeing HBr, and that is not a hydrobromic acid. There is no oxygen over there. There's no 2 other H's over there. There's literally just saying H, B, and R. So, like, I just don't get it. There's like, is there like a little, is it gonna be like a thing where it's like, this is positive, this is negative, so like it'll like do something? Like it's gonna break, this is gonna go into this, and Br with this puts it into this, like the same way it's happening here. So there's a, wait, actually, wait, I think that's literally it. See, if you had Br minus, okay, and now, and forming that's literally just water plus HBr. It's hydroboric acid plus water, but in this case, water is not there, perhaps because it is just dissolved in water? Is that, I mean, am I cooking? Like, is that what's happening? Anyways, tertiary, it's can be heated under reflux with water. Halogen is replaced with OH with alcohol. Okay, this is important stuff. I'm not going to remember any of this. Halogen alkane is heated under reflux with water. Halogen is replaced by OH to give an alcohol. Yep, heating under reflux means vertically less. This happens much faster than the corresponding primary. So you have this plus H2O plus COH plus HBr. So what that means, first you're going to get rid of the Br. Then you're going to have the positive and you're going to get that, you're going to have an entire water molecule binding to it. So you're going to have that carbocation, right? And that carbocation is going to be it's a stable carbocation. And that water is going to literally just bind onto that. And once it binds onto it, there's only one, so it's going to be SN1 in the first step. Now there's a final stage where the product is tied up, where you have another water, and it comes in, and it takes away a hydrogen, leaves it with the OH, turns it into an alcohol, and comes out with an H2O. No, it comes out with an H2O, but the H is a plus. Oh, sorry, it's 3 H's. Oops. Takes an H and gives it a lone pair, leaving it as a hydroxonium ion. The rate of that, and then again, I don't know if this is correct. I gotta ask my teacher, but this is what I really think is gonna happen. So this is obviously a plus, and Br is a negative. However, Br doesn't want that. Br wants this. This is a plus. That means this is minus, and Br is a minus. However, it has this. Wait, Br is a minus. But in this case, O is negative, and in that case, O is positive. I guess that's not it, because I was thinking like this goes here, this goes here, so this is gonna form HOH, and there's gonna be 2 lone pairs plus your HBr. This is the overall rate of reaction isn't governed by how fast halogen ionizes. The fact that water isn't a good nucleophile as OH doesn't make a difference. The water isn't involved. Reaction of secondary. Oh my god, there's a talk through. It's very unlikely that any of we'll ask you about this. It is in the extremely unlikely case that you'll ever need it. The secondary, you use both SN2 mechanism and SN1. Make sure you understand what happens with the primary and tertiary, and then adapt it for secondary. Should ever need to. Will this really help? Because I swear we did this last time and it did not help. What else, dude? We'll read it. We reading everything today. I wish I could show you how many files I have downloaded. Like, it started off as one thing, and now I have like so many documents to describe nucleophilic substitution, some elimination, so many explanations for nucleophilic. There's also explanations for elimination, but that was only one. Then there's some explanations for multiple nucleophilic substitution. Brother. Okay. This one was water. Guides you through nucleophilic substitutions. Honestly, I'm kind of going into these without really understanding what's happening. I'll be honest. For the past two ones, I have not been understanding. Like that one thing. Like I mean, if you're listening, then like, and if you have been listening, then it's kind of obvious where the issue is, and I just don't understand it. Like one would be for that thing with the amines, right? And the other one is this one. Like, where's the BR minus going? You know? So can you find like the? Can you draw the intermediary step? No. I love how it's in the same format as well. This looks wrong. Um, oh wait, I'm pretty sure this is exactly the same explanation as for the one where it's like they explain it for the first time. I'm pretty sure, because I think I'm just wasting time now. I mean, okay, it's like here. Then. No? Where have I read this before? Annoying. Whatever, I guess. Oh. Lone pairs in water will be strongly attracted. Lone pair will repel. Moon goes on. Yep, notice that the oxygen. Yeah, we had this entire conversation when talking about the NH3. How NH3 cannot be like NH4 has to be a plus ion. Can't forget the plus. The movement goes on until water has been attached to the carbon. Yep, notice how the oxygen product ion has. Yep, that charge has to be there for two reasons. On the left hand side of the equation, you start off with 2 overall. Assuming you forgot, yep, that's wrong. Oxygen looks wrong. Oxygen atom is joined to 3 things rather than its usual 2. The oxygen can only join up to 3 if it carries a positive charge. Oxygen with positive charge has the same arrangement of electron as the nitrogen atom, which normally forms 3 bonds. Yeah, wow, that is actually such a fun thing. That's why there's literally like the damn. The organic product is ethanol. The formula is distorted in this diagram so you can clearly see the relationship between the thing on both sides. The other product is hydroxonium ion. This is just a hydrogen ion attached to a water molecule. This is literally what I'm saying. Why do tertiary needs a different one? Because it's bulky, whatever. So first the BR gets broken, so now it's going to be our SN1. It's going to be our first part. So initial slow step, and it's going to be our next fast step. The water part takes place in the fast, and so that a weakish nucleophile like water is involved doesn't significantly slow the overall reaction down. The rate is determined by the slow ionization of the halogen alkane. Yes, it's your first thing that's going to be determining your speed. It's not the second thing. You have made that a point. As with primary halogen alkanes, there's a final stage to this reaction in which a hydrogen ion is transferred. As with primary halogen alkanes, there's a final stage to this reaction in which the hydrogen ion is transferred to the organic ion to the water molecule to the solution. Excuse me? Hydrogen ion is transferred from the organic ion to a water molecule in the solution. What happens is exactly the same as primary. Okay, sorry, there's nothing happening. Again, it's just my reaction with this and the BR that confuses me. The freaking hydrogen, what's it called? The freaking hydrochloric, so hydrobromic acid. Like, that just makes no sense to me. But anyways, we're done. GG, well played. We're done. Well played, gentlemen. Thank you for sticking with me here. It is currently 2:21 and we started, I don't know. So we're not doing this because that's going to be your topic 20, paper 3 or whatever, paper 7. Oh, I don't know. So yeah, that's it for this study session. Cutting it at 3 hours 57 minutes. So I can only wonder how my voice has deteriorated or whatever throughout this entire session. If I move my mic a bit closer, if I could. God damn, man. 1 sec, man. Yeah. So yeah, this was a pretty cool experience. Never done this before. Will I ever do this again? Hopefully. Next on the list is probably going to be mechanics, perhaps, or maybe maths. Oh my god, I had a class today. Am I tripping? What's going on? Wait. I had a class today. Ooh. Oh no, he didn't message me. Faizan, is the PC off? Oh god, okay, this is some personal shit. I don't know. Oh wait, I just leaked my name. Whoops. Well, it's, yep. If you're here for the last bit, now you know my name. Great. So yeah, that's it. That's it for me. That's it for me. I'll see you later.